Hello, everyone. Welcome back to day 2 of OARC 35. On behalf of the program committee, I'd like to welcome you. I will be the session chair and the QA monitor for the first 2 sessions today, up until the long break, and Pallavi Aras will be the timekeeper. We would like to thank both Farsight Security and VeriSign as our workshop sponsors. And without further ado, I'd like to welcome Duane Wessels, his presentation on botnet traffic observed at various levels of the DNS hierarchy. Duane, if you'd like to start sharing your screen.
All right. So thanks, Jake. It's great to be here and be able to interact with all of you, even if it's sort of virtually. My name is Duane Wessels, and this is a joint effort with my coworker, Matt Thomas, who's listening in today. The title of this presentation is Observations on Botnet Traffic at Various Levels of the DNS Hierarchy. So this will be all about this DNS traffic that we see coming from a particular botnet. And here's a little bit of information about the botnet itself. It has thousands of second-level domains and it uses thousands of second-level domains, and a large subset of those are in .com and .net. It has consistent and easily identifiable third-level labels. There's a very obfuscated example there. We see a really even distribution of queries coming from recursive clients. Most of the queries are of type A, and a very small percent are of quad A, and then there's a smattering of other types that you would usually expect. You'll find that some of the things in this talk are unfortunately a little bit vague, and we can't share the botnet's name here yet because there's still some remediation going on at other registries. So we decided to sinkhole these domains, and I want to show a little bit of what things looked like prior to the sinkhole. So this query traffic generated about 375,000 queries per second at the peak of a day to our .com and .net name servers. Most of the domains that the botnet is using hadn't been registered at that time, and so most of the responses were NX domain. A small number of the domains were previously registered and delegated, and some of those we include here, but most not. And as I said, we see a really even distribution of queries. In particular, all the domains receive essentially the same rate of queries. So here's what the traffic looked like over the course of a week. We've got Saturday and Sunday on the ends of this graph, and the weekdays in the middle. And you can see that it varies, of course, throughout each day. The left axis here shows the total QPS, which is that 375,000 number, and then the right shows the query rate per domain name. So like at the peak, we see about 225 QPS per domain. This is what a typical response looked like. The R code was NX domain, and the only data in the response was the .com or the .net SOA record, which has a TTL of 900 seconds. So when we first started looking at this, we were a little bit surprised, and we thought that there must be something wrong. Like in particular, we thought there was something wrong with negative caching. We weren't expecting this level of queries, and so some sort of quick calculations. We said, well, what query rate might we expect if if all these recursive sources were properly obeying negative caching TTLs of 900 seconds, and that came out to be 79 queries per second per resolver source, which is represented by this green vertical line in the graph. And so the data actually shows that 99% of the clients are below that threshold, and so that tells us that the negative caching is working as expected here. You'll see that in the scatter plot, there's sort of 2 shapes or 2 groups, and that's actually because there are sort of 2 variants of this botnet, and they're slightly different. One of them uses more query names than the other. Okay, so now let's look at when we decided to sync all this traffic. We chose to delegate most of the botnet's domain names to our sinkhole name servers, although there was a small group that left undelegated sort of as a control in our data analysis. We used 4 different dedicated sinkhole name servers at 3 geographically distributed sites. The machine's details are there. It was a recent version of Ubuntu and bind 9.16. And that was configured with minimal responses. And we used the good old DNS statistics collector software for our data collection. So this graph shows what things looked like when we switched domains from the initial state to the sinkhole state. The purple line in this graph is the rate of queries per domain seen at the TLD name servers. And again, there's that 225 QPS peak. And then you can see on Wednesday, these got delegated to the sinkhole, and the TLD traffic dropped from that high rate down to about 6 queries per second per domain. And then the green line, it's labeled SLD, that's the traffic seen at the sinkhole name servers, and it peaks at sort of just under 50 queries per second. So we felt that this was a really good opportunity with this DNS traffic to do some different experiments and some research. So we ran a bunch of different things, and one of them we did was to understand how the response code affects caching and query rates, and how does the presence or absence of the requested data affect caching and query rates? How do TTLs affect those things? For the most part, our experiments would run for during the weekdays, the 5 days of the week, and we use the weekends to reset things and change to a new experiment. So here's sort of 5 types of experiments or groups that we did. First is when the response is no error and there is the requested data in the response. So no error / data, the response code is 0. There is a resource record in the answer section, and the TTL comes from that data. Next is no error, no data. And in that case, the TTL, this is a negative response, and the TTL comes from the SOA record. Similarly, we have NX domain, where now the response code is 3, and there's also an SOA record with a TTL. And then lastly, we studied what happens when the sinkhole returns serve fail and refused. So this graph shows throughout the course of a week these 3 different cases of when there's data, when there's no error, no data, and when there's NX domain. It kind of looks like there's 2 lines on this graph, but there's really 3. The 2 negative cases, the no data and the NX domain, are essentially identical. They receive the same rate of queries throughout the course of the day, each day and over the week. In this case, all of the TTLs that we had were set to 24 hours. So that's TTLs on the A records and on the SOA records and so on. So looking a little bit more closely at some of these cases, here we studied the no error with data case with varying TTLs. And by the way, we were able to run an experiment with all these different TTLs at the same time by dividing up the domain names into groups, and so all the queries came at the same time, and we just analyzed the different groupings. So in these graphs, the shaded area represents the daily range, and the points represent the average over the course of the whole week. Note that here the x-axis is the different TTLs represented logarithmically, right? So they basically, each tick mark basically doubles the TTL time. And the top graph shows the query rates seen at the sinkhole servers. So for the lowest TTL of 1 minute, the query rate was about a little under 300 QPS. And then as the TTL increases, the query rate decreases and it sort of plateaus. And you can see here that after about 2 hours, it's pretty flat. There's not a lot of difference between, say, 2 hours and a day or 32 hours. One thing that's kind of interesting is that the choice of TTL at the second level domain affects the query rates seen at the top level domain, shown here in the middle in green, and also at the root servers, shown in blue on the bottom. So Verisign obviously operates some root name servers, but this data has been sort of extrapolated to what the numbers would be for the whole root servers system for all 13. So that's the no error with data case. Here's the no error, no data case. Things look a little bit similar, but the SLD graph in particular is a little bit higher, and you can see that better in an upcoming slide. But again, at the 1 minute level, it's right around 300 still, but it plateaus slightly higher. The TLD and root graphs look pretty similar to the previous one. And here's the NX domain case, which again looks a lot like the no data case, because as you already said, these two cases of negative responses are essentially equivalent. This graph shows those three cases, those three experiments overlaid with each other, and so here you can more clearly see that the negative response cases plateau at a higher level above 100 or just under 100 QPS, whereas the positive responses flatten out around 50 or so. So one thing to take away from this is, of course, that the relationship between query rates and TTLs is far from linear, right? Doubling or having the TTL does not double or half the query rate by any means. So next we studied what happens when you configure the sinkholes to return refused and serve fail. And this was particularly interesting because the first time we did this, we were sort of optimistic, and we configured a large group of domains to be like this, and very nearly essentially DDoSed ourselves out of access to our sinkhole servers. There was so much traffic that we couldn't log in, and the boxes were almost unresponsive. We didn't have out-of-bound access to them, unfortunately, but we were able to recover. And then later on, we did these experiments with much smaller sets. I think this is actually with just 3 domain names. But the numbers here are queries per second per domain. So for those domains that return refused, whereas with like an NX domain, we were seeing 300 QPS. Here we're seeing 40,000 QPS. So a huge increase. And also, very noticeable effects at the top level domains and in the root server data as well. Similarly, this is the serve fail case, and it's a little bit higher than the refused case, but otherwise looks the same. One thing to notice about these, these experiments ran over 2 days, and the first day is lower than the second. That's not because it was a weekend versus a weekday or anything like that. It's just because previously these names were configured, with like 1-day TTLs, and it took a while for the for that data to expire from all the caches out there. So this graph shows the effects of minimal responses. Some of you may have already experimented with this a little bit, but when the minimal responses are on, which I think may be the default, the amount of the received, the transmitted bandwidth is pretty close to the received bandwidth. Those queries and responses are about the same size, but when we disabled minimal responses, the bandwidth usage doubled approximately, maybe even a little bit more. So a few, key observations from all of this. There's really no difference in caching of NX domain or no data negative responses. It seems like, the population of recursive name servers treats those equivalently. For negative responses, TTLs longer than an hour don't make much difference in terms of query rates. And for positive responses, that's about 2 to 4 hours where you don't see much more difference. The refused and serve fail significantly amplify rather than reduce the query rates. And I realized that I forgot to mention previously that the traffic that we saw from the refuse and serve fail cases, we later were able to attribute that to a real small number of recursive operators, and we were in touch with them to explain the problem, and have been told that remediation for that is in progress. So hopefully that will not be an ongoing problem. We hope to be able to do some future experiments using this sinkhole traffic, such as measuring the effects of aggressive DNSSEC caching, understanding or measuring how quickly when a change is made to the parent or TLD zone, how quickly does that change propagate throughout the system, and also to measure what are the effects of having a different set of name servers between the parent zone and the child zone. That's the end of the presentation, and I think we have some time for questions.
Thank you, Duane. I'd like to remind everyone that questions can be asked using the Q&A panel. They'll be read out loud by me. Also, you can raise your hand if you would like to ask your question verbally. And please remember to rate the talk. You should see very shortly a poll pop up. Thank you very much for that. All right, so our first question is from Jeff Houston. Did you experiment with no response at all from the sinkholes?
We thought about that, Jeff, but we did not do that. And one reason that would be a little bit difficult for us is because I don't know of a way to tell bind to just not respond to a particular name. So we would have to, find some other way to do that with some fancy, IP tables rules or something like that. But we didn't pursue that, no.
All right, the next question from Paul Hoffman. Did you have an estimate of how many client sources there were?
Yes, I believe that in this graph, I guess the number's not in here. So if you can count up all those dots, you can figure it out. But I don't remember what the exact number is, but you can see that it's quite a few, maybe on the order of 10,000. Maybe more, I don't know. I'll have to get back to you on that, Paul. Thanks for the question.
Well, okay, we'll quickly go to Audrey Randall. Can you tell us what the purpose of this botnet is? Is it sending spam or what?
It's not a spam sending botnet as far as I know. I actually don't know a lot about the botnet. Like I said, we unfortunately can't mention the name at this point. But I would say that if there are any registry operators that are out there that are interested in this, you can get in touch with us and we can work with you and provide more details to you. But at this point, we can't say more.
Okay. Wes Hardiker has commented, excellent talk, thank you. My analysis has shown that botnets are now spreading DGA traffic over hundreds of TLDs. Do you know if your sinkholing for just 2 TLDs has actually helped the root DNS abuse cause of the problem versus just helping your particular TLD operation?
Yeah, that's an interesting question, Wes. I don't know. I mean, I think that so we were able to sync all this for the TLDs that the botnet uses, that VeriSign also operates. But we didn't look at sort of the overall effect that it may have had on route traffic, and that would be a good thing to do. We should be able, I think with our data, we could go back and do that to look at query rates for all TLDs if we wanted to, all TLDs affected.
Okay, all right. Jeff Houston has his hand raised. I'll allow you to talk, Jeff. Go ahead.
Yeah, it's a little bit quicker to actually ask this one because it's not so easy to type, Duane. We have found in the work we've done that on some days up to 90% of the queries we get on our authoritative servers for a very small domain actually come from replays. That out there someone is capturing some essence of DNS queries and playing it back at very, very high speed. Do you have any feeling of what proportion of queries you're seeing are synthetic and have actually been generated from something other than the original botnet versus original botnet? In our case, the average kicks around long-term. 40% of queries are what I would call synthetic in the long term. Do you have any feel for that in this case?
I don't, and I think that would be pretty hard to do with this particular botnet because it doesn't have like a lot of randomness or uniqueness in its names, right? It uses a very fixed set of both top level domains and second level and third level domains. So I don't know how I would go about detecting replays actually.
Okay, thanks.
From Peter Koch, assume you wanted to sinkhole a non-botnet domain. Do you think the results would be comparable, i.e. how much is induced by the client, how much by resolver behavior?
Yeah, that's a good question, Peter. I think that I think that it would be comparable if you're talking about sort of comparable traffic levels, right? I think like for example, I'm not sure this is exactly what you're getting at, but I'm a little bit hesitant to say that you could apply these results of how the query rate varies based on TTL. I don't know if you could apply that more widely to, for example, domain names that don't get these many queries. I'm not, if that wasn't the question you wanted me to answer, maybe you could try again.
All right, a question from Gavin McCullough. We've seen the difference between negative and refused a lot. Have you come across authorities which, when delegated to incorrectly, insert an authoritative NX domain?
I haven't, but certainly I think that one thing this shows is that there's a little bit of a danger to refused, which is kind of the it's kind of the default for a name server that gets a query for a name that it doesn't know about. In the old days, you would get these upward referrals, and I wanted to test that, but we sort of ran out of time. And yeah, I'm a little bit skeptical that refused is the best thing, in terms of high levels of traffic. I'm concerned about that as well. But I haven't seen anybody insert fake authorities either.
Okay, and we'll close the question queue. Robert Edmonds has asked, was this botnet sending a lot of traffic to the routes TLDs, or did it get sinkholed just because it was interesting?
It was sending enough traffic. So I don't actually know about well, so for our TLDs for .com and .net, it was sending enough traffic that we found it kind of annoying and wanted to move it off of those servers. We wanted to, take some of that traffic away. So yeah, it was not just because it was interesting, it was because it was also an annoying amount of traffic.
Okay, and the last question from Han Zhang. Do you think these two botnets may belong to existing botnet families?
As far as I know, no. I think this is sort of a standalone botnet with just two variants. Perfect.
All right. Well, thank you very much, Duane, for your presentation.
My pleasure.
And we will move on to Casey Deccio. presentation is Behind Closed Doors, a network tale of spoofing, intrusion, and false DNS security. I'd just like to remind everyone that you can use our Mattermost workshop chat for discussions, and as you saw, for question asking, the Q&A poll and/or the raising of hands to ask questions.
Well, everyone, my name is Deccio, and my talk is entitled Behind Closed Doors. This was done in collaboration with students and colleagues at Brigham Young University. So first of all, we often think about access control on the internet. The idea that with a firewall, we might allow traffic from one source, but we might deny traffic from another source because we don't trust that other source. But of course, the big problem on the internet is that identity is not really what we think it is. When some packet is received by Bob, and it looks like it's from Alice, Bob oftentimes has to simply trust that it's from Alice. Now, of course, there are some higher level protocols which help with that, but at least at the packet level initially, Bob has to assume that it's from Alice. But what if that packet actually originated from Mallory instead, and came from where Mallory spoofed Alice's source, and so when it arrived at Bob had no other choice but to accept that packet. And of course, when the response goes back, it goes to Alice. We call this reflection. Okay, now we can extend this model and talk about insider trust. Of course, when you think about inside a network where Bob is a server, Alice is a client, in this model, you'd think Bob would inherently trust clients, including Alice, that are within his own network. And they're more inclined to trust those insiders. But what if the same thing happened where Mallory from some outside network now spoofed a packet claiming to be from Alice, which then crossed the internet, entered that network boundary, and arrived at Bob? That would be problematic. Now, there are two places where you can guard against this type of attack and intrusion. And the first side is, and both of these have to do with source address validation. The first aspect and perspective of source address validation is that which is found at the origin, where the packet originates. And so we'll refer to this as origin side source address validation, or OSAV. And this is covered by BCP 38. The idea is that you shouldn't let a packet out of your network if the source address does not originate from within your network. But the other aspect is destination side source address validation. And the idea is when a packet is coming in that claims to have originated from within your network, you also shouldn't let that packet in because it obviously came from outside. And there's some safeguards against this type of thing within BCP 84. And by the way, a key aspect here is that BCP 38 and OSAV really is meant to protect others from traffic that originates from within your network, whereas DSAV on the destination side, any safeguards you take there really protect yourself. And so there is sort of this incentive model of as to what actually protects self. And the stronger incentive is on the destination side source address validation. So our research question is, how prevalent is the practice of destination side source address validation? Now, of course, the way the DNS works, it really facilitates an experiment like this to better understand what sorts of safeguards are being deployed out there, because it operates over UDP, and it really just takes a single packet being received by a recursive resolver for it to go and do its work in terms of resolution by contacting authoritative servers. And then, of course, the response comes back, but only takes that one packet, one trusted packet, a recursive resolver, to make all that happen. So here's how we set up our experiment. We had over on the left-hand side our experiment architecture, okay, with our sending client, and then a target network on the right-hand side with a destination recursive resolver with some address. And then we also had an authoritative server for a domain that we controlled over in our experiment infrastructure. So the idea then is that we would take, we would issue some query to a given recursive resolver in some foreign network with a spoof source address, such that when the packet arrived, it would look like it came from something within the same network as the recursive resolver. Now, if that actually passed the access control list and the recursive resolver operated on that, that query that came in, then it would issue a query to our authoritative DNS server, and we would issue a response back. And then at that point, the recursive resolver would return a response to the falsified source. We wouldn't see that or know anything about it, but at that point, it wouldn't matter. We would know it had been reached by the fact that we saw a query at our authoritative server. Okay, so that's the gist of the experiment. Okay, and so in terms of identifying the targets, the target destinations, and then the sources we used, first of all, so we used DNS clients that were extracted from 48 hours of root server queries in April 2019. And from these queries, we extracted about 11 million IPv4 addresses from about 54,000 autonomous systems, and about 800,000 IPv6 addresses from about 8,000 IPv6 autonomous systems. Okay, but in terms of sources, what we used, so we used 5 categories of sources that we sent, source IP addresses that we, from which we crafted queries to go to these destinations. And so the first category was what we called other prefix. And that was the idea that within that ASN, it was announcing a bunch of prefix address space. And so we selected about 97 addresses from different /24 or for IPv6/64 prefixes within that same, that were announced by that same ASN, but weren't the same /24 or same /64 as the target IP address itself. We did also announce in the same prefix category, we sent a query claiming to be from one address within the same /24 or same /64 prefix. And then we also sent a packet claiming to be from private address space, so 192.168 and FC00. That actually should have been FD00 from that address space. And then we also sent a packet from using a source address that was the same as the destination address. So that's sort of like receiving a letter from yourself and actually processing it. And then finally, we sent queries from the loopback IP address, just sort of to see if anything would actually pass at that point. And so let's take a look at some of the results that we got. So first of all, in terms of reachability, we looked at 2 things, both on the IPv4 side and the IPv6 side. And so did our query even make it there? We saw in terms of addresses and in terms of networks, we measured these things. So we saw about, close to 5% of destination addresses received a query, but about half of destination autonomous systems included at least one responsive IPv4 address, which was actually really surprising. That was very high to us. And then on the IPv6 side, it was very similar. It was right at 50% of ASNs that included a responsive IPv6 address. In other words, one that was reached by one of our spoofed source queries by the fact that it gave a query to our authoritative servers. We also broke this down just a little bit to see sort of the effectiveness of the different sources that were used that we were guessing, because we had these 5 categories. One of the ones that stood out was the fact that 70% of the reachable IPv6 addresses were reachable. So in other words, when we reached out of all the IPv6 addresses that we reached, 70% of those were reachable by that destination as source, where we had the same source address as the destination address, which was really surprising. But you'll see why that was as I get a little bit later in the presentation. Also interesting, when we broke down, now some of the details are in our paper. So just to show you some of this here. So in terms of exclusive reach, meaning if you were only using this, like if you excluded all other sources and this would be the category that helped bring in some of these sources, we found that 33 of IPv4 addresses were only there because we used this other prefix category. And interestingly, the destination as source category in the IPv6 side, which I just mentioned, almost 10% of those, they were only reachable because we used the destination as source, because those 10% didn't get hit by the other prefix or the same prefix sources. It was just because somebody allowed something in from a loopback address. Okay, let's see, loopback address. There were 22 22 addresses that we found simply because we sent queries from the loopback address. Okay, we wanted to learn a little bit more about these resolvers that we were actually hitting. And so after we determined that a resolver was reachable through our spoofed source queries, we sent 10 follow-up queries to each of these. And that resulted in 10 recursive to authoritative queries to our authoritative server. So what we did with those, we took the raw list of source ports that came from those queries, and then we sorted those. Now this is a simplified version. We're using just 5 ports here instead of the 10 that we did. We sorted those ports, and then we took the maximum minus the minimum, and that gave us a range. Okay, and so we just wanted to sort of look at this range that was being used and plot this out. And here's what we got when we plotted the distribution.
Sorry to interrupt. You have only 4 more minutes to Q&A.
Thank you. Okay, so as you can see, there's a few modes within these graphs that sort of jumped out at us. And I'm going to focus first of all on this, this aspect over here where we had a 0 port range. Now, if you see a port range of 0, that means they answered from the same port every single time, which of course means that there is no source port randomization at all because there is no change in source ports at all. Okay, this affected almost 4,000 resolvers, and of course these are more vulnerable to cache poisoning because of that, and in part because they're reachable through this spoof source vulnerability. And let's see, I'm not going to go through the rest of this for the sake of time, but I'm happy to answer questions about that later. Okay, so let's move along then. We wanted to learn something else about these other sort of high frequency modes that we saw in this plot. And by the way, this lower plot here is actually a zoomed in version of the upper plot. But what we found was different operating systems. When the DNS software uses the ephemeral source port range of a given operating system, then there's a high probability that it'll fall within a certain range. So for example, Linux will fall within this range because it has a certain certain size, a certain pool of ephemeral source ports, and same thing with FreeBSD. This is the range that you would expect to see. Windows is down here. It has about a source port range of about 2,500 by default. And then there's some systems that, some software that don't actually use the OS source port, ephemeral source port range. And so those would be, they use the full range instead, and they would be down here. And of course, for those, we can't identify operating system. But the cool thing is then we can actually look back at these queries that we got, and we can see, the follow-up queries from the different resolvers, and we can actually identify different operating systems. So we can see the number of Windows systems that showed up here, the different Linux systems, the number of Linux systems and FreeBSD that showed up here. And of course, these ones, because they're using the full source port range, we can't identify a given operating system. But it was sort of interesting to break that down, and the full numbers are in our paper. And then the last thing that I'll mention here is that we did some lab testing to understand these last behaviors of, hey, what happens when a packet is received by a given system and it has an address that claims to have come from that system, like on an individual computer, and or it claims to come from the loopback. So loopback's interesting. Windows Server 2003 and 2003 R2 allow things in from the loopback on IPv4, and Linux earlier kernels, so 2.6, 3.3, and 4.4 allow in packets claiming to be from the loopback IPv6 loopback. So that's super interesting. And also of note here, all of the operating systems on the IPv6 side allow in a packet that has the same source address as the destination address. And so the kernel is actually allowing those in and passing them up to the application layer, which was actually really surprising to us. FreeBSD, Windows Server, and all Windows Server also did that on the IPv4 side. Okay, so just in summary, the source address of network packets can't be trusted. We tested DSAV and found it to be lacking in half of measured networks. And just in summary, we have done some reach out, and there's also a self-test tool that you can visit right here that's live. It's sort of beta. We're trying it out, and you're welcome to go there. Thanks so much, and I'm happy to take any questions.
Thank you, Casey. At this time, I'd like to remind everyone that you can rate this talk. A poll will pop up shortly. And if you'd like to ask questions of Casey, please do so in the Q&A panel and or by raising your hand. I don't see any questions yet. So Casey, have we reached out to the maintainers of those operating systems to try to understand why there are differences both between, I guess, V4 and V6 origin routes or destination as source routes?
Yeah, are you talking about this slide right here?
Correct, yes.
Yeah, so that is still underway, but we have not gotten to the point of actually making contact with the kernel operators. We did have some reach out to network operators to talk about some of the behaviors that we found.
Interesting. Okay, we have a question from Roland Dobbins. Can you typify the types of networks where these resolvers were located and reachable? Broadband access networks, enterprises, IDCs on large transit providers, etc.?
Yeah, that's a great question. We started going down that route, and we actually, to be honest, we ran out of space for the part of the analysis we were doing, and I should say time. And so we don't have anything definitive there, but we also wanted to be careful about how we were classifying things since this was going out for publication. But the other thing I will say, one of the tricky parts of this is ISPs. We're still finding that they don't have an easy solution based on some of the access control lists and some of the ways that they have sort of third parties announce their address space. It makes it really tricky to do traditional like BCP 84 type fixes for this. And that's something that's ongoing as to how to reach out and help them with this.
Okay, our next question or an observation from Matthew Lucky. FreeBSD has URPF that would solve this, but you have to turn it on.
Yeah, like a number of things, you do have to turn that on. That's right. Yeah, great point. Thanks, Matthew.
All right, any other questions for Casey? Okay, well, thank you very much, Casey. Oh, I'm sorry, one more question. From Han Zhang. In the spoofed OHR prefix, do you have some of these IPs so you can measure how many reachable resolvers sent to you?
How many reachable resolvers sent to you? I think you're asking, did we save what we did? Is that what you're asking?
Oh, I'm sorry. So in the spoofed other prefixes,
right.
Some of these IPs?
Yeah, I see what you're asking. You're getting back to some of our sources that we use, and I think, are you asking, did we save those away? Is that right, Han? I'm not sure if that's what you're asking or not. We did save all those. We saved everything that we did. I'm not sure if I'm answering your question properly, because we wanted, when we did some reach out, we wanted people to be able to test and see if it was still happening. And so we basically said, here's everything that triggered it before, try it again. But maybe ask me offline, Han, if I didn't answer your question, if I didn't quite understand it.
Okay, we'll close the question line. Brian Dixon asked, is anything about this possible to test via RIPE Atlas probes? Just wondering.
I'm not a RIPE Atlas expert, but I did ask this a few years ago of someone at RIPE, and I believe they told me that spoofing sources was not a thing back then. Plus, you have to have the network that would do it, right? So as a non-authoritative RIPE person, I would say no, but I don't know. I would ask them.
And Matthew Lucky asked, curious if you got any comments, complaints about moving MAC addresses, log messages when you happen to use an address in their network that is live.
Ooh, no, we didn't. In fact, okay, I'm going to answer this more generically though. We got very few people that even noticed this at all. Some people asked about the experiment. Some people asked to be opted out, which we did. One person, the most interesting, when we explained to this individual what we were doing and the nature of the experiment and the reason why, he said, "Okay, I want back in," which we sort of loved. So not everyone was like that, but we only got about five people that even noticed we were doing it, to be honest. And this ran for about 4 weeks to completion. So Great questions. Thank you very much.
Well, thank you very much. All right, with this, I'd like to let you know of the 15-minute break. We will restart again at 2:00 a.m. UTC. You should be reminded that the participants can use the breakout rooms for face-to-face chat. This is enabled by spatial chat. You should have received a link to access that. Do not share your spatial chat link with anyone else. This is specific to you. And once again, we'd like to thank the workshop sponsors, Farsight Security and VeriSign. Thank you very much, and see you in approximately 14 minutes now. All right, everyone. Welcome back to OARC 35, Day 2, Session 2. I'd like to welcome Chris Mikkelson to give his presentation on DNSTap updates.
Hello, I'm here today to talk about some recent changes and some open work in DNSTap. For those of you who aren't familiar with DNSTap, a quick recap of what DNSTap is all about. DNSTap is a flexible, structured binary log format for DNS software. It supports both real-time stream and file-based processing workflows fairly equally well, with a lot of shared code between the two. And we designed it for minimal overhead on the instrumented software. The early reference implementations were non-blocking, so if the reader wasn't keeping up, the server would keep on going. As such, it's not really useful, really good, oriented towards like audit logging and similar, but more for like stats collection and telemetry and other observations, more operational. The binary format is defined by a protobuf definition at the link URL here. The streaming and file format is a library that Farsight developed called Frame Streams, which is a lightweight streaming protocol, system negotiation when done over a network connection, but the file format is basically the unidirectional stream that is negotiated. We support two implementations, one in C, the reference implementation, and a Golang implementation at those sites. The primary focus of DNSTap is exporting the DNS message as it is seen by the submitted server. It can export other things, but we haven't defined those yet. Along with the message, it exports relevant context, such as the IP address that it came from and similar. And of course, the definition of relevant evolves over time. So we've maintained this specification via primarily discussion on a mailing list, which is information about which is available at dnstap.info. The first update we've done recently is adding support for new protocols. So the context has always included some protocol info, a bunch of enum type fields. So whether it's IPv4 or IPv6, and the query port and response ports to the ports, and in order to make the ports make sense, a protocol UDP or TCP. This did not leave out, this did not include DNS-over-TLS or DNS-over-HTTPS, which are coming into more wide use. And those are definitely not adequately captured by TCP, because DNS-over-TLS and DNS-over-HTTPS are quite a bit different from just plain DNS-over-TCP. After a short discussion about a old suggestion late last year, we added values to the socket protocol for DNS-over-TLS and DNS-over-HTTPS. That led to a few open issues, which are still open, which we might want to close at some point. So DOH is definitely not just a trivial thing on top of DNS over TCP. So we're blurring some protocol layering here. In particular, DNS over HTTPS uses 0 for the query ID, or recommends that strongly, which means that if you're writing an application that's trying to match up queries and responses with the query ID, you need access to the HTTP2 or HTTP3 stream ID, which is not included in DNSTap yet. And similarly, like, you might want to know what HTTP version is there. So we might need some more features fields to capture these details. And that, of course, leaves out other protocols like DNS-OARC or DNSCrypt or other experimental protocols. Do we want to include those in socket protocol? Yeah, that is something that is open for discussion. The most significant update was adding policy reporting to the to Dnstap. So it's been a while since you could safely run a recursive DNS server for a community of users and just let it let it blindly resolve everything without exposing your users to various bad actors and other badness on the internet. In the olden days, it was fairly customary to just publish an empty zone at your recursive DNS server. But that does not, that's a fairly coarse mechanism, and it's obviously advanced since then. So there have been a number of efforts, one of which is response policy zones that are a non-trivial mechanism for enforcing policies and processing of DNS messages. So we wanted some visibility into this. So earlier this year, we added a policy field, which is a compound type, which includes information about what rules were triggered, what identifier in the packet matched the rule, whether it was client IP or the queried name or any number of things, and what action was taken in response to that. This was written primarily to cover the RPZ use cases that we had. We made sure we covered the RPZ actions and the RPZ identifiers. And part of that was because RPZ is a well-known mechanism with rich functionality and is well documented and covers many, if not most, use cases for policy filtering. We made a nod to supporting other mechanisms with a policy type string, and if there are actions or identifiers that other policy engines use that we want to report through Dnstap, we just need to add those. I'll finish up with some general housekeeping notes about other open projects. So we have a couple of open issues on the dnstap.pb GitHub from a while back for adding cache status for what information or whether a query is answered out of cache or out of authoritative zones or out of cache miss iterative queries. And then also a generic message tag for tying multiple Dnstap messages together. These, as I mentioned, have been open for a while. There are some open discussions now stalled for a while that proposed multiple different implementations with no clear consensus on which to adopt, if any. I would like to reopen those or close these issues at some point. Another open issue is JSON format for Dnstap. The protobuf binary format is a bit of a barrier to entry for a number of users. It's not something that there are a lot of command line tools to slice and dice and process. And we've had a few submissions of JSON output to various Dnstap tools, and those submitted JSON formats are not necessarily compatible with each other. So I think there would be a good use for a standard JSON binding for tool independent workflows. If any of this sounds interesting to anybody listening, I would like to hear from you, preferably via the mailing list or unicast or in the break room. So with that, I will open the floor to questions.
Thank you very much. Our first question is from Roland Dobbins. Has thought been given to implementing Dnstap as an IP fixed interface extension or full-fledged standardized format like PSAMP? This would make Dnstap much more accessible and allow for much easier combinatorial analysis with other forms of flow-based telemetry and open up greater possibilities in terms of analysis tools.
So if I understand the question, it's about implementing Dnstap with a different source from the actual internals of DNS software. can Roland confirm or deny or confirm this or correct me on that?
Yeah, as an IP fix or IPFIX extension, enterprise extension, or full-fledged standardized format like PSAMP.
The focus of Dnstap is definitely as a plugin for the DNS software itself, and as its own thing, rather than as like part of a overall ecosystem like that. So I would say that's not on our radar, but I would be willing to discuss that more.
Okay. Follow up to that from also Roland. The question is whether thought has been given to implementing Dnstap atop IPFIX. DNS software could export it via IPFIX.
I have to confess, I'm not really very familiar with IPFix.
Okay.
So that is.
All right. Casey Deccio has raised his hand. Casey, you should be good to unmute yourself.
Yeah, I'll make it quick. So one thing you asked about if there was, interest in making the JSON available, and the answer is yes here, because I know I've written some parsers that take the frame buffer and put it out a different way. But my other question is whether there's any way to, and if this is ongoing work, a way to take the buffering and decrease the time delay, like when you don't have a full buffer, to putting something out from your F-string capture. I don't know if that's the same as what you're talking about in just a protocol buffer or not, but I thought I'd ask about that. We can take it offline if it's not applicable.
In general, the implementations that we support or that we're familiar with try to get the data out of the instrumented server as quickly as possible. So there is a ring buffer primarily to absorb back pressure from the consumer, not keeping up as fast, or not keeping up with the processing.
Okay, another question from Willem. Are there any plans to standardize this work in the IETF?
There were more than plans. There was actually an effort to make an internet draft of this. Some of the complications of this that were it being based on protobuf, which is not an IETF standardized protocol, and we have an installed base, so switching to CBOR or similar was not very practical.
Okay, it looks like that is it for questions. Thank you very much, Chris.
All right.
All right, our next presentation is from Siva Kesava. Presentation is, so you think your name servers are correct, finding errors automatically in name server implementations. Siva, if you want to share your screen.
Hello everyone, I am Shiva Kakarla, a fourth-year PhD student at UCLA. Today I'm going to describe you a way to find errors automatically in nameserver implementations. And this is a joint work with Ryan Beckett from Microsoft, with Madwell, Todd, and George from UCLA. So we all know how hard it is to implement a nameserver that is efficient, has high throughput, and is correct. DNS name resolution seems simple at high level, but over the time, it has evolved into a complex and intricate protocol. As Jeff Houston said in his AppNic blog post, the DNS is a remarkably simple system. You send it queries, you get back answers. However, the DNS is simple in the same way that chess or Go are simple. They all have constrained environments governed by a set of rigid rules, but they all possess astonishing complexity. Those rules are embedded in the English documents called RFCs. The developers must understand these RFCs first and then transform into a working code. This whole process is delicate and errors can happen and has happened in the past, like any software system. But the errors in DNS have far-reaching effects due to its global presence, which puts the developer under a lot of pressure to ensure that there are no exploitable crashes or no wrong answers are written by the software. Similarly, they also want to ensure that they are doing what most others are doing, so as not to have any interoperability issues. Perhaps the most important requirement is ensuring that the developed software is compliant with the RFCs, that is functional compliance. Does the developed nameserver software follow the logic and procedure as indicated by the RFCs? Are there any cases on which they differ, and why do they differ? To check all these issues, each implementation currently has its own test suite. Each implementation developer manually writes some tests to check the lookup logic, RFC compliance, and whether the response returned is expected response. This is all good and has got a lot of errors in the name servers. But it is an onerous task which puts a lot of burden on developers to come up with good tests that stress test many corner cases of the DNS RFCs. I have recently started working and researching on DNS topics, and after seeing this current testing scenario, I and my collaborators thought, can we do better and reduce burden on the developers? The short answer is yes, but how? Our key idea is to generate tests automatically, thus avoiding the laborious and manual way of writing tests. To know what is the expected answer for a generated test, we can simply compare the response from multiple implementations. When one or more DNS implementations disagree with others, we flag this as a potential bug. Our tool, which automatically generates tests, compares the response from multiple implementation, is called Ferret. But how to generate high coverage tests that identify functional correctness errors? So to note that, first I will give an overview of the end-to-end design of the system before delving into deeper of how we generate the tests automatically. So we have RFCs, and we leverage RFCs to drive test generation, a technique called specification-based test generation. Using this technique, we produce tests that cover many distinct DNS nameserver behaviors. While the end-to-end behavior, so the tests are basically like a zone file and a query. So for example, this is one example test case that the tool generated. So there's a small zone file of 3 records, and this is the query that is supposed to be sent to that zone file. While the end-to-end behavior of DNS query lookup can require contacting many nameservers, we employ a modular approach that only generates tests for a single nameserver in isolation. In the case of DNS, nameservers keep no internal state. The response they provide is based solely on the zone files that they have and the input query. And the tests are not tied to any source code. So Ferret can generate tests for any implementation because these are basically zone file and query. They can be used to generate tests and test any nameserver implementation. Okay. So now we have the test generated, and we want to test them, and we want to test multiple implementations using them. As many parts of the DNS RFC are either underspecified or not specified, and there is not always a definitive right or wrong answer for these cases, we, instead of comparing the responses from different implementations to the RFCs, we compare the results from the implementations to one another. When one or more implementations disagree with others, we flag it as a potential bug, and we look into it why there was a difference. And this module, we call it as differential testing module, an idea commonly used in compiler testing. So now first we look into differential testing modules, some details, and then we will look at some examples of the bugs that we found, and then into test generation module. We compared the behavior of 8 popular open source authoritative implementations of DNS, and the table shows the 8 implementations, the language they are implemented in, and a brief description of their focus or how they are used. For testing implementations, Ferret uses Docker to construct a working container image of each implementation. To generate the image, we clone the implementation's code as of October 1st, 2020 from their open source repositories available on GitHub or GitLab. Ferret starts a container for each image, and each container serves one zone file at a time as an authoritative zone. The containers expose the DNS port 53 to the host system by mapping an unused host port and enable the host to send queries and receive responses from the DNS server running in that container. This way, each implementation is given a unique port that maps to the container's DNS port 53. Finally, Ferret uses Python library DNS-Python to send queries and receive responses from the containers. And these are all the list of the bugs that we found. We found around 30 bugs, and most of them have been confirmed, and a lot of them have already been also fixed by the developers. And I will give you some of the examples of the bugs that we found. So consider this example where this is the test case that the tool generated. Both the zone file and the query was generated from the tool. For this query, it is first rewritten using the DNAME to the CNAME to the new query shown as above. And the new query will match exactly the DNAME record. Now, when this test case is used to test bind and others, all the others responded with a synthesized CNAME and a DNAME as a response. But we found that bind was not responding and the query timed out. We inspected the logs and found that the server has crashed by giving this message. And we reported the crash, and we noticed that it was an easily weaponizable denial of service vector, and it can be remotely exploitable. It can be used to crash both the resolvers and the authoritative servers. And it also affected all currently maintained bind branches. So we initiated a responsible disclosure, and recently, just a few days back, a CV was released with a high severity. To again emphasize, this is the test case that the tool automatically generated, and we just knew that because of the crash, we know that there was something wrong in the bind, and there was no manual process in any of this. Okay. As a next example, consider this one more test case, where there is a wildcard CNAME, and the target of the CNAME is also can be matched by the wildcard again. So the query is first rewritten using CNAME to foo.example, and foo.example will match the wildcard again. If care is not taken, then you will just go into infinite loop of matching the CNAME over and over. So we tested it with Core DNS and all the remaining 7. All the remaining Core DNS is a popular open source server in Go, and it's a recommended server for Kubernetes also. All the others responded with a synthesized CNAME as response and detected the loop and stopped. I'm sorry. But Core DNS did not give us any response. We again noticed the logs, and what we saw was that finally Core DNS keeps looping and looping and almost takes all the resources available on the system and finally crashes with this message. If there is any hosting services that use Core DNS as the DNS software, then this is a serious security vulnerability. An attacker could potentially upload zone files that upload a vulnerability like this one, compromising the service by crashing the provider servers. We informed the Core DNS, and they fixed it by adding a loop counter. They also mentioned that for now it's important to protect the server rather than to give client a valid answer. As the next example, let's consider a performance bug in bind. So this is another test case where there is a delegation for foo to ns1.campus.edu, but ns1.campus.edu is also under campus, but is a sibling domain to foo. And there is a sibling glue record for ns1 for foo. So for this query, the response from PowerDNS not in NSG was that they responded with the NS record and also gave the glue record in the additional section. Bind did not return the glue record. And when we asked bind, the first response that we got was that this report turns out to be very interesting, and here is what they managed to find out. Bind uses a glue cache to speed up the identification of glue records, but it had 2 unrelated errors. If the cache lookup fails, then glue records are supposed to be searched for in the zone file, but they were never searched. And glue records for sibling domain name servers were accidentally never searched at all, so there was no chance that this A record would have been written by the bind. And it's an open issue on their GitLab, and it's on their June 2021 milestone. Next, let's look at one more example in NSG where we found a data structure bug. This is another test case that the tool generated where it inserted a wildcard character in the RData side of the CNAME. Response from NSG was no error, and the CNAME was given out. But the expected response was supposed to be NX domain because www.star is under under books.online, and that domain name does not exist. So the expected R code is NX domain. bind not and power DNS return with NX domain as CNAME target does not exist. And our code is important, as we all know, like resolvers can use to determine whether domains exist or not. And when we filed the bug report, NSG responded that it has to do something with the internal data structure, and there was some flag missing out. And they have fixed it, and it's all available on the GitHub issues. As a final example, let's consider this zone file and the test case. So there is a DNAME, and the DNAME causes an infinite loop because it rewrites to something which is actually the prefix of the original domain name. So query is rewritten using DNAME to www.us.corp, and this new rewritten query will again match the DNAME, and the length keeps increasing. And this leads to an infinite recursion. In this case, the implementations are free to choose how they will respond. It is important that implementation guard against these cases, which can otherwise lead to heavy resource consumption by the name server. Bind applies DNAME multiple times and stops when limit reaches 17. Power DNS just returns surfail in this case. Not and NSG apply DNAME only once. Works here, but had to be applied multiple times when there is no loop. And we reported those cases, and both NSG and NOT fixed those issues. An interesting byproduct was that we found an error in the NOT test suite. NOT had a test suite that compares the responses with bind to follow bind, and they had a comment mentioning that one of the tests is for DNAME loop, like the one above. Unfortunately, they did not construct the zone file correctly, and the error led to having no loops at all. So that was the error they had. Instead of increasing the target, they decreased it, so there was no loop found because of that. When reported, the developers agreed and fixed it. And the fix was they went with a single response, like they use DNAME only once, unlike the 17 for as the binders. So we have seen all the examples and what can be done. So what is lurking in this test generation module, and how do we generate those test cases automatically? So we use the RFCs, and from the RFCs, we have earlier built a formal model of the name server semantics. It's like a mathematical specification of the lookup logic. Like it's a declarative model of how the lookup has to happen, and we built it from the RFCs, mainly the 1034, 4592, and 6672. Now we perform symbolic execution on the model. Symbolic execution is a static analysis technique that enumerates execution paths in a program and uses. So this is a path. So for a query and zone to end up at even branch, you need an exact match followed by whether the records are authoritative. And if there is an exact type, then you take this branch. So these are the 4 constraints that need to be satisfied if you want to take that branch. And now we put these constraints to an automated constraint solver to produce an input that will take each enumerated path, thereby generating tests that cover many different program behaviors. To actually do the symbolic execution on the mathematical model, we made an executable version of the formal model, and it is implemented in Zen, a domain-specific modeling language embedded in C# with built-in support for symbolic execution. So we took the RFCs, built a mathematical model first, and then converted it to an executable model. Now we symbolically execute the model to generate the test cases. The test cases are basically a pair of zone file and a query. And after the test cases are generated, we use it in the differential testing module. And these are the statistics of the number of tests generated for each branch. Because symbolic execution does not scale for large large sizes of the domain names, we constrain that the zone file will have not more than 4 records, and the length of the domain names are also less than 4. So there are around 10 branches that we found in the lookup logic, and these are the total number of test cases generated for each branch. And now we have the test, and then we put it through all the one test case at a time through all the 8 implementations, get the response from all the 8 implementations, compare them, and group them. If there is a single group, then there are no issues, like all is good. But if there is more than one group, then there is a likely chance that one of them is misbehaving. So we had 12,000 tests, and out of them only 4,400 had respond. Out of them 4,400 made a single group. There were 8,000 tests in which at least there was one implementation which differed from the rest of the others. But that's too many to check manually. And there are generally typically orders of magnitude fewer root causes for these deviations. So we do a kind of fingerprinting. We fingerprint each of the failed tests to group, and so that we reduce the number of test cases that we need to inspect. So these are the statistics of the number of tests for each model and the number of tests failing for that model case. Model case is basically the branch in the formal model, and even basically is like exact match when there is an exact type also. We fingerprint the failed test, and a fingerprint for each test leverages both the specification based and the differential testing, and then groups test by fingerprint. So for each failed test, we use the model case due to which it was generated and the unique implementations in each group from the responses. For example, this is one example of a fingerprint. In this test case, the test case was generated because of R1 branch, and on this test case, NSD, NOT, Power DNS, and EDIFA had one response. Bind and Code DNS had one response. Trust DNS and MyDNS had a response, and the three responses were different from each other. And the reasoning behind all of this is it's unlikely for different unique bugs to have the same fingerprint. Now, after we do the fingerprinting, we end up with almost 70 fingerprints, a reduction of more than 2 orders of magnitude. And some fingerprints had only one test, some had 4, and some had more than 10 test cases. And we inspected all the fingerprints that had 4 or fewer number of tests. And for the other ones, we randomly sampled the test from each fingerprint. Once again, this is the total list of the bugs that we found by inspecting the failed test cases using the fingerprinting technique. Out of the 30, almost all of them are confirmed except 2 in Code DNS, which I filed and they haven't responded yet, but there are also some issues in the Code DNS. And in the Mara DNS and Trust DNS, there are a lot more issues that we found, but we haven't reported them because they are missing out some features, or they don't have some of the features implemented. Now, this is all good. And now if you're developing a new DNS software, how do you test using this framework? So all you need is first generate a Docker image for your implementation. Start a container with a host port mapped to port 53 of the container. And you need a small script to stop the server running in the container. Modify the configuration files that you need to. For example, for bind, you need to change the name.config. For not, you need to change the Lua script. So you need a small script to change this and restart the server. And then now it's your choice to pick from the 8 implementations that we currently have, the ones that you want to compare your implementation with. The Docker makes it quite simple to test new implementations and also add any existing implementations that currently support DNS authoritative logic. And so now the Ferret model as of now is there is a test generation module and then there is a differential testing module. But what if you want to test a custom test? It's simply you need to just plug in before the differential testing module and it will all work. But the more interesting case is how about how do we test for any implementation specific behaviors on our zone files? Let's say I have UCLA zone files. I want to know, is there any implementation on which these zone files will cause a difference? So you have zone files, and to test them, you need to use Groot. Groot is a tool we built earlier, which can generate query equivalence classes. And I won't go more details. Please see our paper or tool for those details. Now you can pick one query from each equivalence class and then test using the zone files. This way you can also check your zone files to see if there are any differences among the implementations. Finally, from all of this, these are the lessons that we learned. Like, no two name servers agree completely on all the test cases. And nobody agrees with the RFCs also perfectly, like there is no 100% match. RFCs do the job well, but there are some gaps and ambiguities. For example, it's in RFC 1034, it's stated that CNAME loops should be signaled as errors, but at what point or whether it should be unrolled at all, should the loop RRs be returned at all? For another example is, can I synthesize CNAME from DNAME is a perfect response to a CNAME query. When RFCs are open to interpretation, implementations make choice based on performance, resource constraints, and safety. For example, in the CNAME loop case, power DNS returns are failed. Others unroll the loop up to some point and return the unrolled loop. So the interesting point here is, like, should the resolvers account for these different choices, which will make the resolvers more complex and lead to interoperability issues? Or should the RFCs be more verbose and stringent and mention all the cases perfectly well? To conclude, I presented our tool Ferret, which can automatically generate tests for nameserver implementations, and it generates high coverage test suits, stress testing many corner cases of RFCs. And we use differential testing to compare multiple implementations, and we tested 8 implementations, found 30 new bugs, and both the Ferret and Groot are available on GitHub, and you can reach me at this email. Thank you.
Fantastic, Siva. Very impactful work. Okay, we have, I want to remind everybody that you can ask questions in the Q&A panel and or raise your hand if you would like to ask your question verbally. Our first comment from Peter Van Dyke. This is awesome. Thank you for this work. And thank you for your very clear bug reports, both to us, Power DNS, and to other projects. Joe Abley is asking a question. I'm sorry, not a question. This is insanely great. I agree, really comprehensive and useful.
Thank you.
Jacques Latour is saying, did you say you generate the tests by parsing the RFCs automatically?
Yes.
Interesting. Okay, Vicky Risk has asked, I was skeptical at the beginning, but I agree, this is great. I love the comparison between the implementations. Is there a list of which RFCs you analyzed to create your test cases?
We mostly analyzed CNAME, DNAME, A, Quad A, and SOA, NS record types. So that basically is 1034, 6672, and the wildcards is 4592, as far as I remember. So these are the 3 others that we took into account.
Okay, we have a follow-up question from Jacques Latour. He asked a question about how you are, he's asking how did you parse the RFCs to do that automatically?
Okay, I think probably it's better. We didn't parse the RFCs, so we read the RFCs and then we manually converted them into formal model, and then we encoded the formal model in the Zen language. So we didn't automatically parse the RFCs, we just read it through, understood, and then converted it into a mathematical formulation.
Okay, we have a couple raised hands. We'll go first to Shivan Sahib. Shivan, if you want to unmute yourself.
Sure, yeah. This is fantastic. Just a quick question. I tried looking on GitHub for some sample test cases that you generate. I couldn't really find any. Do you have like a dump of what a test suite would look like somewhere?
Oh, I just made the code public, but I did not make the test cases public yet. I can do that. Okay. I think this is just working. We are submitting to a conference. I did not make everything public yet.
Okay. Yeah, I just wanted to take a look at what the test case format looks like, and what's sure. An example one. Yeah, but otherwise, this is great. Thanks.
Thank you.
All right. Brian Dixon asks, do you have employment lined up yet? He's half joking and wants to say awesome work.
Thank you. I'm still in 4th year. It'll probably take 1 or 2 more years to graduate.
All right. Any other questions for Siva? Okay. Well, thank you very much, Siva. Again, this is amazing, not just as as a tool for quality assurance and finding differences in the software, but it's, as far as I know, one of the better tools out there for the fingerprinting of DNS servers, which we used to be able to do well, and over the last few years, not so much. So it's super great that you were able to achieve this.
Thank you. Thank you. Thanks for all the good comments.
Okay, our next presentation will be from Allison Mankin and Giovane Sahib. Shivan will be on the screen first, and the presentation is Planning and Deployment of DNS Zone Transfers over TLS. Shivan, if you'd like to share your screen.
Yes. Hello, everyone. My name is Shivan, and I work at Brave Software. And but this work was done at Salesforce. I'm here today with Allison Mankin, and we'll be talking about planning and deployment of DNS zone transfers over TLS. Also wanted to give a shout out to our co-authors, Willem, Pallavi, and especially Sarah, for whom right now is an ungodly hour, so she couldn't be here, but thanks to her especially for driving this work over the past little while. And alrighty, and I'll be giving the first part of the talk, and Allison will be giving the second part. Okay, so for a little bit of background, why do we need XFR over TLS? So currently, like many parts of the DNS protocol, or at least until recently, the zone data transfers were unencrypted. So zone data could be collected via passive monitoring on the wire. And zone data can be sensitive data, and especially for larger organizations. So for several reasons, policy, regulatory, you might want to keep your zone contents as a transfer between primary and secondary private. So that is the main motivation for XFR over TLS, to prevent zone data collection during transfer. And our proposal for this is encrypting DNS zone transfers, so both AXFR and IXFR, using TLS as a transport. And the use cases are confidentiality, so putting it over TLS would defeat the zone content leakage problem. Authentication is a big one, so we can use single or mutual TLS authentication between the client and the server, the primary and the secondary, which can complement TSIG and access control lists. And also performance, because the current usage of TCP for XFR is often not great, and we'll be going into that a little bit more detail. And just to give a quick status update, it is an IETF draft, and it is now in the later stages of review before publication as an RFC. And there are multiple implementations and deployments are being planned, and Allison will be talking more about that later on. So just to give a quick description of what this would look like. So on the left-hand side, you can see there is the IXFR request and response happens over UDP or DCP, and this kind of happens in clear text. And we're proposing that you put the IXFR request and response, which constitutes a zone data transfer in a TLS session, in a long-lived TLS session, we optionally also suggest that you can put the SOA request and response, but we did a threat analysis and we consider for the purposes of this draft, like the really sensitive data is really the zone data. So that's crucial, and optionally you can also add the SOA request and response. We mandate that all XFR messages must use TLS 1.3 or later. We have port 853. We mandate the usage of that, just like DNS over TLS, although you can negotiate a different port. And servers are free to use other queries on a ZOT connection. So we are not in any way mandating the authoritative DNS over TLS support. To do this, you can use extended DNS error code not supported, which is now a published RFC. And we also go into some detail in the draft around the various different operational and policy options you have for managing ZOT connections. And historically, XFR has been somewhat basic when it comes to TCP usage. So earlier specifications actually had implications about using just one connection per XFR message. And this was updated somewhat for AXFR later on, but Zod draft updates specs for both IXFR and AXFR to recommend efficient usage of TCP. So we recommend multiplexing XFRs, even for different zones on the same connection, pipelining queries and out of order responses. And we also recommend the usage of eDNS0 keep alive to keep the connections open for reuse to improve performance. And we went into some detail in the draft talking about the authentication mechanisms. And here you can see that we kind of try to see what are the properties that we would like. So we would like data origin authentication, channel confidentiality, neutrality, and channel authentication for both the secondary and the primary. And the security mechanisms that we have for that are TSIG, TLS, and there's a few different options for TLS, and then ACLs on primary. And the draft recommends that, or mandates that, the secondary must always use strict TLS, so you get channel confidentiality and authentication because the server is authenticated. But the primary can use MTLS, which is preferred. So in that case, the client is also authenticated, and you get the confidentiality from the TLS session. But you can also use IP, ACL, along with strict TLS. And I'll be handing it over to Allison now to talk about implementation and deployment status.
So this is about the implementation and deployment status. The key thing for us is that that protocols, sometimes we expect them to kind of deploy themselves. We have spent a fair amount of time during this whole process as part of the IETF's more hands-on and hackathon process, working hard with implementations, working hard with operators, asking them how they might deploy this, getting a sense of the realities of trying to use this in the field. This has allowed us to be able to say at the time of near publication, the ISG is nearly finished with approving this. There's just a couple of revisions to make, that we have a lot of like preparation for deployment. So first of all, on the implementation front, Bind worked with the team, with the author team at hackathons and other ways. Sarah worked with them on helping to provide some requirements to provide a support for the ZOT in a good form in 9.17, which is a development branch. We are in discussion with when it will be backported to 9.16. We expect it to be tested. There's some more work to do, but we expect it to be available in a production capability in a time frame that is pretty practical, pretty pragmatic. Unbound has been involved, and NLNet Labs Unbound has been involved in this work for the whole time. Willem is one of our co-authors, and Unbound itself has the ability to do part of ZOT, which is the secondaries AXFR side. We have also worked with NLNet Labs to prepare PRs against NSD, which are more complete, which include client side and server side ZOT support, connection reuse as well. The PRs are planned for inclusion in our latest discussion with Willem in the 4.3.7 release. So there's a very concrete plan there as well. We expect to have, we did a lot of interop testing at the IETF 110 hackathon, and we'll be doing it again at the 111 hackathon with Bind and NSD and Power DNS, and also with some other of the operator players. Next slide, please. In terms of operations, diverse managed DNS server operators are important for ZOT because that's people arranged to have some heterogeneity in their XFRs. Bind and NSD were featured in particular in the work that my part of the team did, because operators had a use of those particular stacks. So Ultra DNS, the New Start company, has a service which is oriented towards TLDs called XTLD, which is based on very plain bind servers. PCH, which provides a very large number of secondary services, uses bind and NSD. So we get a lot of practical clout from making a fairly complete service in those two implementations. Both of those vendors have been open, both of those operators have been open with a commitment that they will offer ZOT in a product form when the implementations have reached product level. And we want to especially flag that PCH has a very strong set of privacy first policies, and that when they get to the point that ZOT can be a product, they expect to make it a default offering for secondary service. Eventually, as customers get more interested in it and express more interest, it might even be something that they would consider making mandatory as a way of emphasizing their privacy first approaches to operations. Next slide, please, Shivan. There's some challenges when you deploy. We define a transfer group as all the servers involved for transfers in a given zone. Could be multiple primaries, there can be multiple secondaries from multiple operators, different implementations. And it's quite important from a security standpoint that you not have a weakest link, no weak point there. TSIG, TLS, decisions, single or mutual, IP ACLs, those things should be consistent across the transfer group in order to make sure that there isn't one particular server that transfer which is more visible or is easy to catch from an adversary. So the challenge is, how would you configure and enforce and test all that? We expect to spend time in the hackathon working on that. There's a lot of interesting issues, and that's one of the things that we hope to do from this talk, is attract more attention and interest, because we'd like for people to work with us. Next slide, please. The further deployment challenges are that that you can't expect an all or nothing rollout, but we are actually pretty strict about what's required in order to have secure ZOT. So you can expect that.
Sorry to interrupt, Allison. There are 3 more minutes till.
Thank you, Pallavi. You can expect to have a incremental experience for a while, and then say at some point you've reached full ZOT. We need to have all secondaries having a client-side implementation. That's one reason we focused on that. Not all DNS operators have a lot of experience with certificate management, but we think that's actually a feature, not a bug. And there's some other paths, such as dynamic updates. Next slide, please, Shivan. In breaking news, the IESG pointed out to us that there's a recent IETF directive for Alpin to be required. Alpin is the application layer protocol identifier in TLS. And so ZOT will use Alpin equals dot. We don't think this applies to old stub, to recursive dot, because it was before, it predated that. I think we're short of time, so let's skip over this talk, this particular bullet. So in summary, ZOT will soon be a new IETF standard. There are implementations, people are planning offerings, there's ongoing work, including the upcoming hackathon. We didn't mention, but padding is an important feature for getting really good privacy. And so new work is starting up on that, and also on the encryption that you would do for dynamic DNS update. And please contact us in the ZOT channel and OARC Mattermost, and feel free to join us in the hackathon upcoming at IETF. And now I think it's time for questions.
Wonderful. Thank you, Shivan and Allison. Our first question comes from Joe Abley. In the comparison of different authentication mechanisms, doesn't TSIG provide channel auth and not origin auth? A TSIG secret is specified to a single edge in the transfer graph, but that edge is not necessarily bound to the origin, unless I misunderstand what you mean by the word origin.
Right. Yeah, so TSIG is not, I guess we were trying to say that it is bound to more like the data side of things. So one party is saying that, you know, it's a pre-shared key in a sense. So that is what we were saying. It's not like an endpoint, unlike a TLS connection where you're saying that this particular endpoint is making the is making the connection, and if you know that that is verified, then you can like authenticate against that. But I think I missed the first part of the question.
The first part of the question was, in the comparison of different authentication mechanisms, doesn't TSIG provide channel auth, not origin auth?
Well, so we consider channel auth as in like literally being the channel between the two parties, like the server and the client, or the primary and the secondary. So yeah, in that sense, we were considering TLS to be providing that, not TSIG per se.
I could speak to that a little bit further. That actually came up in the ISG review. I don't know if you've caught up with all of that. In fact, there isn't origin auth because the IP address is not covered by the authentication, and so it is possible. It's actually, I think, intended that you could have multiple channels, as Joe said. So TSIG is not. TSIG combined with TLS provides you a better situation in terms of with a form of TLS authentication. But that's why we require a form of TLS authentication. We actually require strict authentication. And then if you have the strict authentication in place, you actually will also be covering the origin, the IP address origin. But we actually, mutual auth will be better for this purpose. So I hope that's clear enough. The spec is actually has a lot of material on that topic, so you can read up a little bit more on it.
Okay, Paul Hoffman has a question. Paul, if you wanted to unmute yourself.
Thank you. So Allison, great. However, you skipped over the one slide I wanted to hear most about, which was the last one on ALPN. Simply because I'm wondering how much is, like, I could not keep up with the traffic on the list of what was going to change in the draft with respect to ALPN, and how much is this going to affect implementations if you're changing what the ALPN is. So if you can go back and give a bit more detail, that would be great.
Yeah,
Thanks.
could you roll that slide back for us? Thank you.
Yep.
So we think that it's a few lines of code to say in the TLS that alpin equals dot. We are expected to use the same alpin as any other dot, in particular a dot. We won't have an issue, and so then the question is, how do you distinguish if you're running both? And the hidden primaries, which is often what you're using in the case of XFR. Will not have that problem because they won't actually be serving a dot. They won't be serving queries. But you also have the option of running ZOT on its own specific IP address or port, which is something that you can agree on in that transfer group, which gives you some flexibility about this as well. But bottom line, this discussion, which was all public on the IETF list and on the DNS privacy list, on the DNS privacy email list, is that alpin equals dot for all the dot families, and definitely is going to be there for ZOT. And we don't think it's a lot of extra code to do that part of the work.
And we also spoke to a couple of implementations, and they seem to be fine with that as well.
Yeah.
Okay, so and this won't have a negative effect on the fact that, as you had showed in earlier slides, there's already a lot of implementation. You're not concerned about this late change causing incompatibilities and such.
If it wasn't quite as late at night, I would have mentioned what Shivan just said, which was we went back to all of the implementation teams and asked them about it, and also including Peter from Power DNS, and that was not a big concern to add this particular to add alpin equal dot and use that part of TLS.
Very good, thank you.
Yeah.
All right, I see no additional questions or hand raised, so I would like to thank you both, Shivan and Allison, for your presentation. And with that, we'll pass things over to Keith Mitchell. Keith?
Yeah, thank you, Jake, for your session chairing for the last two sessions, and also to Pallavi for timekeeping. And thank you to all of our speakers. We're once again absolutely spot on time. There's some really good talks for the first half of today. Additional thank you. I'd like to thank our sponsors, Farsight and VeriSign. And we're now going to take a break for 90 minutes. So a chance for you to eat whatever meal is appropriate in your time zone, which is a midnight snack in my case. And you can hang out in the spatial chat. So there's that's the platform that you used yesterday. You will see instructions for how to join that if you didn't get them already in the rolling slides. So we will be restarting at 4:30 UTC in 90 minutes time. See you there.
Hello, everybody. My name is Willem Torop, and welcome back to this third session of OARC 35. First of all, I'd like to thank our sponsors, Farsight Security and VeriSign. I also like to point out that the timekeeper of today will be Huyen. And then without further ado, I would like to welcome our first speaker, which is Benno Overeinder, who will present on keeping up with the IETF in the DNSOP working group.
Welcome, my name is Benno Overeinder, and I will keep you up to date with activities in the IETF DNSOP working group. It's covering quite a span of recent proposals, progress, and current working group drafts and finished works. So given the time, I will not go into details, but just will whet your appetite for more. Good. This is the DNS universe in the IETF. You see some faint stars, you see some bright stars, but the activities in the IETF are here in the stars with a red circle. I will primarily touch upon DNSOP and also mention some of deep dive work. Good. Let's go to business. Finished works. So work that has been finished during the last DNSOP working group meeting at the IETF 110. What was finished is the message dices for DNS zones, zone MD. So zone MD is securing zone transfers. Think of DNSSEC protects resource record sets. Zone MD protects zone as a whole. Think of, well, you can validate the zone, the file and its origin, authenticity. Typical use cases are, for example, small zones being transferred to resolvers, for example, this root zone or response policy zone. So for large and dynamic zones, this scheme is not yet suitable because of full validation or verification of the zone. Other work that has been finished recently in the DNSOP working group is Nameserver cookies. It's actually an update of an already existing RFC 7873, but it updates actually for this RFC for interoperability in any CAS setup. So in any CAS setup with multiple implementations, there were some operational issues that some of the cookies generated by one implementation could not be interpreted, were not the algorithms, the hash algorithms used, were not supported by the other implementation. So RFC 9018 corrected this. DNServer cookies gives some protection against DDoS attacks or cache poisoning. And it gives you a lightweight DNS transactions mechanism. Good. So this is work that is just recently finished. Work almost finished in DNSOP. In working group last call is the SVCB HPS draft or the service binding a parameter specification in the DNS via the DNS. This has been already presented by Ben Schwartz in the previous OARC meeting. It gives you a new family of types of records that allows a client to learn more about the endpoint and the service provided. Think of TLS or HTTPS. In that, it also improves security and performance. And think also, because the other endpoint, the service, can provide some information about the endpoint. This also enables aliasing of the Apex domains. So think of the long-standing discussion of CNAME in the Apex with SVCP, HTTPS resource records from the service binding draft. This can be specified and enabled. So that's this very nice result here of the working group. Other work that's for working group last call is DNS transport over TCP operational requirements. This is both for unencrypted TCP as well for encrypted TLS sessions. This document also asks for feedback. I'm sure that John Christoph asked for feedback on the DNS operations mailing list. So please, well, it's in working group last call. So please give some feedback here. And it's still very valid thing here, because recently we had a discussion on our mailing list that an unbound user couldn't resolve his domain. And he thought there was some error here. No, but it was actually the case that he, I don't know why, he thought it was not necessary. He disabled TCP support in the unbound, and his answers were, well, his zone was signed, answers were too large, and he get the timeout instead of, so he didn't expect this behavior. Joe Ebley also reacted on the mailing list that this is also good feedback probably for the draft. And the people are, TCP is really required for proper operation of your precursor and name server. Good. I have to speed up a bit. Close to working group last call is the revised IANA consideration for DNSSEC. So historically, it's kind of an administrative rectification. So previous RFCs mentioned about, give some requirements for DNSSEC algorithm, but forgot to mention to say something about the DS hash algorithms. So this is in this draft rectified, and the motivation was that with the introduction of national crypto algorithms like GOST, it doesn't need to go through the IETF standards track. Right, close to working group last call is closed. Sorry, closed, not close to. Closed is the DNS query name minimization. It's the it's a BIS document of RFC 7816. Given the practical experience and deployment of DNS query name minimization, this document has been rewritten and updated. So will be submitted soon to the ISG. And other documents that has been closed working group is NSEC and NSEC3 TTL and NSEC aggressive use. Due to a combination of unfortunate wording on earlier documents, the aggressive use of NSEC and NSEC3 records may deny names intended longer than has a longer intended lifetime of a denial than intended. Sorry. This document changes the definitions of NSEC and NSEC3 to correct that situation. More work of active drafts in the working group. So we have DNSSEC, DNS catalog zones. It's it's a provisioning mechanism by syncing configurations from primary to secondary. And it does so by transferring a list of zones administered by the primary and sent to the secondary. Instead of having changes at the primary and also manually changes at the secondary, because it's not the zones that run at the primary are not necessarily directly automatically changed at the secondary. With VSEC of DNS catalog zones, this can be automatically kept in sync. The authors ask for operators for use cases and feedback. There's at the Mattermost OARC instance a channel on this work. So if you're interested, please join the channel at the Mattermost server. Another draft needs work in the DNSOP working group is DNS avoid fragmentation. So what's the max size interval of UDP packets? So there are a number of sources. So RFC 4035 defines, well, IPv4 should, must and should at 1220 for IPv4, IPv6, and 4000 should. But DNS Flag Day last year introduced a recommendation of 1232. This was really an operational kind of, this was a value that worked very well in operational environments. Jeff Houston did a number of measurements, measuring the DFD, the DNS Flag Day, and he came to some other values as a recommendation. So it doesn't seem that the DNSOP working group comes to one specific value, but to a range, to the interval of valid, of reasonable values. This discussion will also be kicked off at the DNSOP working group mailing list to settle on a sensible range. And I will also send emails to the DNS operations mailing list of the OARC and the right mailing list for input from operators. Good. Speeding up a bit here. New work.
Sorry, but you have 3 minutes remaining until the Q&A.
Okay, 3 minutes?
Yes.
Yeah, okay. I really want to speed up here. This is also a discussion that NSEC 3 iterations, consideration, also discussion kicked off by Victor Duchovny on DNS operations mailing list, and it's also have a look at it. There are, well, typical values, very high number of iterations. These are not necessary. So there's a proposal for lower iterations also by the draft of Wes Hardeker. DNSSEC automation has been presented yesterday by Ulrich Wisser. Next slide. Moving to deep-drive work. This also has been presented, zone transfers over TLS. It's submitted to the ISG for publication. Other, I find very interesting work here at the deep-drive work group is DNS over QUIC. So again, this is not the same as DOH with HTTP3. So here's QUIC, the transport layer. So you don't have the HTTP headers and cookies. So there, I have copied here the table of the implementation status of DNS over QUIC. I won't go into detail. This is table from a presentation by Sarah Dickinson. So there's a good work going on already here. I'm looking forward to more results and progress of the document. Right. Existing work, more existing work is, of course, at the deep drive, lots of attention is going into encrypted DNS from precursor to authoritative. So it started in February, March. We had one document specific on this recursive authoritative DNS with encryption. And today, this document There was already another document, but today this document has been refocused to recursive to alternative with unauthenticated encryption, and 2 new documents actually working all together, defining the common features of encrypted and unencrypted, of encrypted recursive to authoritative DNS, authenticated, sorry, or unauthenticated, and a draft by Erik Scola and others about signaling authoritative DNS encryption. And here SVCB can be used to discover whether the nameserver supports encryption. So that's also a nice result of the DNS of the SVCB draft in DNSOP. I will skip this one. It was a long time discussed, oblivious though, in deprive, but it's now concluded that it's for now going in the individual track, in the individual submission. Oh, not too bad. Here, that's one. This is interesting. Confidential computing to protect DNS resolution. So this was a presentation at DNSOP by Yari Arko, and was not DNSOP work actually, but it needed a platform, and at DNSOP working group we provided some time to present his ideas about confidential computing to protect DNS. So we always discussed things about securing DNS queries over the network, but DNS data at rest should also be protected. So here I just copied the slide from Yari. So the DNS resolver is executed in a trusted execution environment, so that the hardware or the platform owner cannot access DNS data at rest at the server. There was quite some interest in the working group, but also it's not in charge of DNSOP. So for now, if there's some progress, something to present, there will be room, but probably it will need to find another working group or another place to be worked upon, maybe in the IETF or in one of the other, somewhere in the DNS, or somewhere in the DNS ecosystem universe in the IETF. That's it. It was really very brief in time, but also it was extended in the number of topics. I hope you have learned about activities, the DNS activities in the IETF. I'm open for questions, for more details, for more pointers. And I also invite you all to join the discussions on the DNSOP mailing list, or when we spin off some of the discussions at the DNS operations mailing list of the OARC. Thank you all.
Thank you, Benno. I think we have 1.5 minutes for questions. I also like to remind the audience that during the Q&A section, a poll will show up, and this is the only time you have the opportunity to rate the talk, and this is quite important to the PC and the speakers to do this, so please take that opportunity. I see one question in the Q&A facility of Zoom from Andrew Kempling. He says, I'd also mention the ADD working group has adopted 2 drafts on DNS discovery, with a further draft in development that covers split horizon DNS. And the TLS working group continues to work on the ECH encrypted client hello draft, which may provide a longer term solution for ESNI, encrypted server name indication. It has implications for content filtering. Finally, the consensus on oblivious DAO in deprive seems to be to keep it experimental and focus instead on oblivious HTTP.
Yeah. Thank you for the additional comments. Yeah, Andrew Kentling. That's correct. Yeah.
I have another question, remark from Ralph Weber. What about the camel, given that you barely could fit naming all the drafts in the presentation?
That is true. Yeah, yeah. So what about the camel? It's so DNSOP is actually, of course, not per se extending. It is working on drafts for operational for DNS operations, and we run into well, operational problems that has to be solved. Think of the RFC, the DNS server cookies. These were really not useful with the old draft of the old RFC. We needed to update the RFC, and the same for the QNAME. Again, these are the BIS documents. But for SVCB, for example, this is it might be part of another straw on the camel's back, but it does solve a lot of well, operational, I wouldn't say problems, but challenges. That's better. We really needed this, and this draft opens up a lot of well, possibility of solutions where we had a lot long discussions before in the DNSOP working group before that. Yeah. Okay. So it's always a balance between, is this not not the final straw on the back of the camel, or do we really need to accept this work?
Is still standing.
Yeah.
Good.
Yeah.
Okay, thank you, Benno.
You're welcome. Thank you.
Yeah, could you stop sharing the slide deck? And then I would like to welcome another Dutch guy. Actually, most of the complete session is Dutch, luckily, except for our timekeeper. So Otto Moerbeek, welcome.
Hello. Let me set up things.
We'll be presenting TCP fast open, not so fast. No
okay,
problem.
Thank you for your introduction. I was, well, having some trouble here, but I can start now. So my name is Otto Moerbeek, and I'm going to talk about TCP fast open with the subtitle Not So Fast. So today, what I will be discussing is how I added TCP fast open to the PowerDNS recursor. I'm a PowerDNS developer and mostly working on the recursor. So we're going to look a bit at some programming issues, but also mostly practical issues with the TCP fast open. And I hope to show that TCP fast open is indeed fast, at least faster than no TCP fast open, but it is not fast in all aspects. There are some issues with it. So to start, I'm talking about why TFO, why is it relevant to DNS? And then I would like to tell something how it works, and then look into TFO from both a server point of view and a client point of view. Of course, authoritative servers are only servers with respect to connections, but recursors are both servers and clients. They are clients to authoritative servers. And then look at the practical issues encountered while using TCP fast open, and then some conclusions. I see there's a typo there. I'm going to also try to do some suggestions how to improve the current situation. So first, I'm going to discuss why TFO, and especially why TCP is relevant in the DNS world. Well, as you all know, DNS queries, or rather DNS answers, are getting larger and larger. We have text records, we have DNSSEC records, we have EDNS options, all added to the payload of a DNS answer. And that will, so the cases where a answer does not fit a UDP buffer size will increase. And especially since current situation is that to avoid fragmentation in the UDP world, the buffer sizes originally suggested are now suggested to be much smaller than before. So the DNS protocol has to switch to TCP to get the answer to the client in more cases. And that's already being seen by operators of recursors. Much more connections are using TCP. Now, the overhead of TCP is an issue. It consumes more resources both on the client side and the server side in terms of computational effort and memory. Things like both client and server have to keep track of state of the TCP connection, and also to actually transfer data from the server to the client and vice versa. More packets have to be exchanged. So the TCP, a typical TCP answer retrieved over TCP will have a larger latency than an answer over UDP. Now, TFO, TCP fast open, does solve some of those problems. Especially it solves some of the latency issues at the cost of using even more resources. A bit. It's not that much, but it does consume more resources than just doing regular TCP. So before we look into TFO, let's have a brief overview of probably something you have already seen in other places. This is the classical TCP connection setup, data exchange, and connection teardown sequences shown by Wireshark. So the three-way handshake, SYN, ACK, and ACK, followed by a query sent to the server. That query is ACKed by the server, and then followed by a response. This is actually the response, the data that is the client requested. Then we get an ACK from the client to the server to acknowledge the reception of the query, the response, and then we get a teardown of the TCP connection. So in total, 10 packets are exchanged to get the query and the answer transferred, and compare that to a typical UDP or the UDP query response, which takes 2 packets. It takes 4 packets for the actual query to arrive at the server, and 2 more packets. Sorry, it takes 4 packets for the query to arrive, 2 more packets to get the response back, and then some maintenance packets to tear down the connection. So that is the reason why the TCP connections has a larger latency. More packets are exchanged to keep track of the state of the connection. So in the TFO setting, the initial data exchange isn't that much different. If the client has never seen the server before, and the server has never seen that particular client before, the initial packet of the client will contain a extra TCP option which says, well, I do support and I request from you that you send me a fast open cookie. That TCP option is embedded in the first SYN, and in the reply to the SYN ACK, the server will respond with, okay, I also do support fast open, and I'm sending you a cookie. That cookie is a secret based on some client properties, like particularly the client's IP and the local, but also on local server data, like the local IP of the server and port, and also, most importantly, a secret. That secret is a secret the server uses to compute a hash of the data I mentioned, and that computes to a value of the cookie, and that cookie is sent back in the response to the SYN. So after this, the client has a extra data, and it will use that for step 2 in the TFO. That is a second or further connection to that same server. The client will send, with the initial request, initial SYN, immediately the data and the cookie. That cookie will be used by the server to validate that indeed this client, I've seen this client before, it has done a proper 3-way handshake before, so now I'm going to accept that the client sends data immediately with the first SYN. And not only is that data accepted, but we will see that also that data is immediately transferred to the application. So normally data in the initial data from the query is only sent to the application after a 3-way handshake completes. But now it can be sent to the application immediately on receipt of the first packet. And you see that we have now total 8 packets, and the query arrives at the server immediately with the first packet, and the answer is contained in the 4th packet. So we have effectively reduced the latency quite a bit. Now, why is that cookie important to be cryptographically secured? I'm going to briefly mention that. It is important because otherwise there would be a possibility that for a SYN flood attack, a new type of SYN flood attack, the RFC goes into more detail, but effectively what you want to know is that the client did a proper 3-way handshake before. And if it does so, if it has done so, the server will send that cookie as an acknowledgement of that fact. And the client can present that later on to say, well, I've been here before, you know me already, I've done, and I'm a proper client because I'm able and willing to participate in a proper 3-way handshake. And actually, that's all the cookie says. It doesn't say a lot more. That's, of course, that's a pretty weak form of authentication. So the cookie itself is no actual proof that the client is the one you're talking to. It only proves that you have seen that particular client before. If you want to know more about it, why how this is important, please consult the RFC. So the sketch of the implementation of a TFO supporting TCP stack is pretty simple, and the nice thing is the server doesn't work, the client doesn't work. It's all not very complicated. It becomes a bit more complicated because you also want to have, of course, graceful degradation, in the sense that if one of the sites does not support cookies, things go right. So there is some complication there, but the nice thing from an application point of view is that the OS does all the real work, generating the cookie, storing the cookie for later use in the client, and on the server side, validating the cookie and generating one if it's needed. So for my application point of view, application writer point of view, things are reasonably simple. So let's see how does that work out for various open source DNS servers, both the authoritative and recursors. And what we see is that both most of them mention TFO support in release notes. But if you go look into the details, it becomes a bit vague. Is it always enabled? Do you have to set a option? How does for recursor, is there any, are we talking about the server side of things or the client side of things? Of course, the recursor acts often in a way of a client to authoritative server. So there is support, but things are a bit fake. We'll see that later. Also illustrate that with one other example. So I'm going to talk mostly about the client side because that's the thing I've worked on in the recursor. But a quick look at the server side. If you want to do support TFO, there's only one thing you have to do in the code, and that is to set a option on the socket, on the listening socket, and that's enough. You would assume, but there's more to it. One is you have to also enable it in the OS if we're talking Linux. And the thing is, even the socket option call does not fail if it's not enabled in the OS. So you can think that fast open is enabled, but actually it won't be until you set the proper sys control on the OS level. This is documented properly in kernel.org. But remember, if you want to serve, enable TFO as a server, you have to also set that sys control in Linux. And I would recommend that servers would warn that TFO is enabled for the application, but not on the OS side, if that's the case. Otherwise, system administrators might think TFO is enabled, but it is actually not, because the actual set socket option call does not return an error if the OS disallows it. So that's the server side, one single set socket option call. There's a small detail, and that is not it's not well documented. It's the set socket option call is not a Boolean, but a number, and that the number reflects the queue size of the work incoming TFO requests. And there is actually I found no guidance in the proper value of that queue size. So that is something which I think the documentation should improve on. But now look at the client side. Client side is also pretty simple. When I was looking at this recursor, our DNS recursor already had the server side side of things. So we're looking into the client side of things, and luckily it is also pretty simple. There are actually two methods of doing TFO as a TCP client. One is to not do a connect at all, but use a specific socket option in the send, specific flag in the send system call. Alternatively, you can also enable it before you actually do the connect to a server. And then if your code is doing non-blocking IO, which I think most recursive servers do, then there are actually no real other code changes needed. It does not sound difficult at all, and but there's also there is a drawback, and that is this particular set socket option call is not documented at all. If you want to know how it works and how to use it, you have to look up the pull request into Linux where it was introduced, and which explains how to use it. So that is a bit of a drawback. It seems that TCP or other network socket options are generally not documented at all, or very sparsely if they are newer than what is mentioned in, let's say, Stevens or so. If it's too new, you have to go hunt sometimes for the documentation, or even look at the source code to actually find out what it is doing. But actually, once you've found that out, it is not that hard. So next comes testing. And I was a bit surprised that the code wasn't working as I was expecting. I looked at the Wireshark diagrams and I saw strange things. And well, one of the reasons was that I was using a TCP forward to quad 8. And quad 8.
Sorry to interrupt, but you have 2 minutes remaining until the Q&A.
Okay, quad 8 uses, is this 20 minutes? So the Q&A, sorry.
You have 5 minutes for Q&A, but you have 2 minutes.
5 minutes, okay, yeah. Okay, so the problem is that quad A does accept cookie requests. It does send back a cookie. So here you see in this diagram that the TCP fast open was presenting a cookie it retrieved earlier, but then quad A refuses the cookie, sends a new cookie, and the client does a retransmission after that. So quad A is supposedly doing TFO, but in practice it does not do it properly, and this is caused some head scratching. And I looked a bit into this, and the summary is quad 8 is not the right DNS server to check your TFO operations. It does send cookies, but it does not accept the same cookie. In very rare cases, it does accept it, but only if you hit the same Anycast server by accident. And the strange thing is there are solutions to this problem, which Google did not implement. And you can have two ways of solving this issue, either by setting the TFO secret used to generate cookies on a system or OS level. You can also do it on a specific listening socket from the server side, but both are not implemented at quad 8. So it advertises TFO support, but does not implement it properly. This issue is known at Google for a long time already, since 2017. And what is a bit sad is that both the TFO RFC and the Linux implementation originate from Google. So they have all the knowledge. I would assume they also have the resources, but for some reason they do not support it properly. This is also observed at Google's authoritative servers. Of course, that is the issue I was most concerned with, because I was doing the recursor to authoritative part of the problem. For the DOT and the DOH offering at quad 8, they do that correctly. So they know how to do it, but for some reason they have not implemented that for both the authoritative servers and their recursor servers for clear text TCP. Other public recursors do support it, but only for DOH. And the nice thing is, if you do a DOT or DOH connection, is that TFO allows you to send the client hello immediately included in the first packet. So that is nice. Authoritative servers are very rare, their support. There's more detail in the paper I mentioned. And since there's now already quite some years, it has been available in the Linux kernel. It seems a bit low, that numbers presented. So it would really be nice to do that study again and see if more authoritative servers do support TFO. But this is not the only issue. There's also an issue on the client side. The Linux kernel is doing all the work, but it's not doing all the work always. If you look at packet captures, and in data reported by Dnstap, you see a lot of open active fails, but also open black hole counters increase. These counters are not documented as far as I know, but looking at the source code in the Linux kernel and some descriptions are found on, by Googling, it turns out that the Linux kernel is extremely conservative. Effectively, if a single TFO connection times out, for whatever reason, just maybe because the particular authoritative server is not available, it will stop using TFO for all connections for an hour by default. So that means that if you have one authoritative server which does not respond over TCP, even authoritative servers you tried to connect to and that worked before will now stop using TFO for 1 hour. And if it happens again, the period is even longer. So there's an exponential backoff. Well, in practice, hitting authoritative servers with issues happens a lot and is not rare at all. So that means in practice, we are seeing that even if you have TFO enabled, in practice, the protection mechanism, so to speak, kicks in and TFO is disabled by the kernel. Why would it be so conservative? And I guess that is because, well, maybe you are in a situation where some middle box does not allow TFO because it does not like this particular option. It does not know that particular option. And some middle boxes are very strict in that. So it will kill the connection, drop the packets. And that has the effect that it just stops working. So I think we can come to the conclusion that TFO as a technical measure does work. It is faster than no TFO, but the adoption is very slow, even if the kernel does all the work and the introduction into an application is pretty simple. So the adoption is slow because of the conservative client approach, lack of documentation on the server side, both in the kernel and in DNS servers. So it's all the nice things are there, simple implementation, completely done by the OS, almost completely done by the OS, but still adoption is very slow. And that's a bit of a pity because I think, well, it could at least lighten some of the drawbacks of TCP. And I would say that the aggressive non-use of TFO in the Linux kernel should change in that respect. And also the documentation on how to set it up properly, but the sys controls, etc., should also improve. And then it maybe has a chance to get some traction. So that is, I think, the conclusion.
Thank you, Otto.
Thank you.
I'm afraid we are now also out of question and answer time.
Yeah.
Maybe
I'm sorry about it. I made a mistake in my head with the time allotted. So
yeah. I know.
Yeah.
Time flies when you're having fun. But maybe Dinesh, you can put up the poll window very quickly to rate the talk, because it's the only opportunity to do so. And then I take this opportunity to just read out a remark from Puneet Sood from Google. Google Public DNS, the TCP fast open feature fell through the cracks, not intentional. Also, Otto, I invite you to answer the remaining questions from Brian Dixon in the Q&A feature in Zoom.
Yeah, I'll do that.
So we can continue with the next talk, so, which will be from Giovane Maura. And Giovane will talk about fragmentation, truncation, and timeouts are large DNS messages failing to bits, falling to bits.
All right.
Go ahead.
So, all right. Good morning, evening, or afternoon, whatever, depending on where you are. Thanks, Willem. So yeah, this is work we done at SIDN Labs. Me and Moritz and Marco, Martin as well, and Christian, who's also at the University of Twente, also in the Netherlands. We're going to look today into fragmentation, truncation, and times out, and while DNS messages are falling to bits. I mean, Jeff Houston has been doing like lots of work in this field, and this was actually inspired by his work, and also by I saw that the DNS flag day was coming along, and I thought it was a good opportunity to have data from a different vantage point on the same issue. So that's actually the start of this presentation, and actually was a paper that we published at PUM 2021. And if folks are interested, you can actually download them in this link. So this I don't really have to cover much because everyone knows all these things here. Because DNS knows the core protocols in the internet. But if UDP fails, if the message is too large, if it gets truncated, what happens is resolver should retry using TCP. But the problem is it's with large messages over DNS over UDP. Vanilla DNS over UDP supports maximum 512 bytes. Over TCP, there's no strict limit, but eDNS 0 extends this limit to much higher levels for UDP. But if the response is too large, what can happen is, for the network, if it's too large in the network MTU, the packets can be either fragmented or discarded. And well, Jeff Houston has been covering this for a long time. It can lead for unreachability. And actually, there was also a study from the Neonet Labs on that, I think over V6 specifically. We also cite that. And the server, what it can do if this response is too large, it can truncate, and the client can then ask it via TCP. But the question we analyze, we are interested in here is how big is this of a problem on DNS based on the data that we have. And we have data from a CTLD, the Netherlands .nl. What you're gonna look, what it did in this research is look into 3 different months of data from 2 of our authoritative name servers, July 19, July 20, October 2020. And here in this table, we have the entire breakdown. You see that like roughly 2.93 to up 7.15% of the queries are actually UDP truncated. You see here the ratio of TCP. Ideally, they should be similar, but I'm going to get later into that why some TC UDP queries are not being followed up. So in total, we get 169 billion queries and responses. I mean, queries and 164 billion responses from unique 3 million IP addresses and 46,000 autonomous systems. And these are the questions we want to analyze. How come on our large DNS responses? How come it's truncation on our server side? If resolvers also fall back to TCP? And what is the impact of flag day 2020? So the first question we analyze when analyzing this data is to analyze the response sizes that came out of our servers for the DNS zone. And we found that virtually all the queries pretty much, you can see here in the CDF, are smaller than 1232. 1232 is right here. So you see that pretty much everybody here in the CDF, in regardless of UDP of the server or TCP, are smaller than 1232. And that's the limit that was chosen by the DNS flag day. And you may say, well, that's because it's .nl, it's one CCTLD, you cannot generalize that. Well, a resolver service from Google reported 99.7% of their own queries are smaller than 1232 too. So it kind of confirms our view as well, and over both V4 and V6. The other question we look at is like how often server-side fragmentation occurs. So since our vantage point is passive authoritative server, we cannot really know what happens in the network between us and the client. We just look at what gets fragmented by us, and we see that on the server side, there's very little fragmentation. If there is any fragmentation going on, is on the network, but we cannot really see that very easily. And we get less than 10,000 queries a day from 2.2 billion daily on that. So it's not like a lot of queries being fragmented on the server side. What about in-network fragmentation? So since our vantage point does not allow us to see that, we ran two measurements with RIPE Atlas, and we had like, in this measurements, we have this number of active probes on both measurements, sending this number of queries. And the difference between the large measurement and the small is this response size. One has 1744. These are responses that run on the DNS of .NL, the .NL zone, and the one had a very small response size. And what he wanted to know is like, what is the percentage of queries that time out when you retrieve smaller answers about this size from RIPE Atlas, and is this number. And I mean like using RIPE Atlas directly to query our authoritative server, NS3, and not using resolvers. So for some reason, 2.5% of all the queries that go to NS3 from this 8,500 probes get lost. But if you amplify that to this, use a larger response size, you see an increase to up to 7%. So the differences should give an indication of what's being fragmented and lost in the network. But you cannot be 100% sure because you don't have the full view of the network. So what about the network fragmentation? That's just pretty much what I just repeated there. We just see the responses of the clients, but the figures that we found as numbers here confirms peer review studies. And the next question we analyze over this research is how common is DNS truncation? Well, truncation occurs when the response is too large to be sent by the server to the client, and the server just truncates it to a certain limit and flags with a TC flag on. And as I said here, that depends on the data set we're looking at, but it's between roughly 3% to up 7%, depending on the P version of the data set you're looking at. And the queries we're looking at, they're querying it truncated at this value. And we also identify in the paper that large DNS zero buffers do not prevent truncation either. And so we also wanted to know how many queries that are truncated, how many of them are actually followed up by TCP queries. And we found that the details are in the paper, but we found out that roughly 80% to 85% of the queries, depending on where you're looking at, they're actually being followed up by TCP. Well, we all know that there's a lot of strange behavior on DNS, so maybe some resolvers are not standard, but the details are in the paper. And we also look at where the most common advertised eDNS values by clients. This is the data set of July 2020. So we get all the queries for that month, and we get all the DNS zero values that they plot. And you see that most resolvers here are using the 426 DNS zero value. Some they're just using 512, and there's a large distribution over here. So, and here distribution per autonomous system. So 4096 is still pretty popular. That's the conclusion you can get here. And Bind, and I think maybe other resolvers too, I'm not quite positive, they don't use a fixed DNS zero value. They use one and they keep on changing that value depending on the server, increment and increasing, depending on if they get an answer without truncation or not. So this figure here shows the number of unique DNS values per resolver. And you see like roughly 70% of all the resolvers just announced one DNS value to us. But we see like the others actually, like above here, they send at least 2 DNS values. So the same IP address is using different values, but most just an advertised one. So DNS Flag Day 2020, that was a project initiated by the community, and the idea was to get like folks to avoid at any cost fragmentation. And one way to do that was to use the eDNS buffer size, which would actually limit it would reduce the chances of truncation. And a value of 1232 was chosen for that. There's a lot of reasonings for that. The idea is, so if you would use your resolvers to advertise that value, you could like eliminate problem fragmentation and reduce truncation. And the idea is like, what was the uptake? We wanted to see that using our data, and to identify that, we compare the data that we have from July 2020, that was before the flag day, in the entire month of October 2020, right after the flag day. And we plot the CDS here, the distribution of all the responses that we get based on that. And you see that the curves, they pretty much overlap to each other. And that's a sign, apologies. This is a sign that there has been not significant changes up to October 2020. And we actually look into the data, and we found that 11,000 resolvers pretty much changed from whatever values they had to 1232 actually. That was the value recommended by the flag day, and you see that the values that where they came from. So it's not a large number of resolvers that actually changed that. So we see that maybe we need to measure more often. Maybe to measure like now or in a couple of months from now to see the uptake. But right after the adoption of right after the flag day, we didn't see much uptake. We described some networks that actually did that. We could clearly see that in our data, but still, there hasn't been that many as we would have hoped for. And to summarize what is seen here, this is pretty much a summary of what we've seen in the paper. The question is, are the DNS responses falling to bits? Well, from our vantage point, we found that most DNS responses are actually small, so there's a little fragmentation risk from our vantage point. But we see that could happen as well. And the server-side fragmentation is minimum, but in the network we measure using Rapid Atlas, that actually happens. 2 to 7% of the .NL UDP responses get truncated, and out of those, 80% to 79 to 85% are followed by a TCP query. And the flag day uptake was not very noticeable yet, but again, we need to probably measure this again in more detail to see that. Yeah, and I think that's what I have to say here. If there are any questions, I'll be happy to take them.
Thank you, Giovane. That was really quick.
Yeah.
Thank you for that. Yeah, we do have a bit more time for questions. So I'd like to point out again that during the Q&A section, a poll will show up where you will be able to rate the talk, and this will be the only opportunity to rate the talk. So please fill in your questions in the Q&A section, or raise your hand if you want to ask a question live. I can see one raised hand, but I'm not really sure. Oh, Jeff Houston. Yeah. Okay. Jeff, if you can unmute yourself.
Yes, I have. Great presentation. Thanks a lot for giving it. We also looked at the flag day and what actually happened with resolver behavior. And I think, like you, we're looking at the interaction between recursive resolvers and the authoritative servers. Yeah. In our case, of course, we were seeding this environment with our own queries. So we kind of understood why our authoritatives were receiving queries. The point I would actually like to make is that we did see quite a visible change of the average behavior of queries. Now, presumably, if, say, the Google public DNS recursive resolver changed its behavior, then all of a sudden a whole bunch of queries are going to change because a lot of folk use it. But I am just going to focus on user counts, not resolver counts, because it's easier to think about. What we found was that actually the big uptick was not 1232. That was a relatively small but still visible uptake. The big uptake was a bunch of resolvers that went to 1400. And it's sort of, okay, I can see that you're taking flag day to heart, but where did 1400 come from? It's sort of, well, you could have gone even higher if you wanted, but why 1400? So I just wanted to point out that recursive resolvers did make a change, but the change was almost unanticipated. But as I said, great talk. Thanks.
Thanks. And thanks, Jeff, for pioneering this work. See the CDF here can see the green line of October. We see no spikes around 1400, but I can look clear in the data and let you know if we actually can identify that. But yeah, I agree with you. We haven't seen much uptake, but I will look at the 1400, let you know. But from the graph here, I cannot really clearly see that.
Don't forget that I'm measuring what I would call users, and I'm not sure, but I think you might be measuring resolvers.
Yeah, we getting like resolvers that talk to us, and you are getting the correct me if I'm wrong. You're doing the ad networks, and you're getting the resolvers from those networks of the users, right?
Right, but the issue is when we talk about resolvers, we're never quite sure if we're talking about Jeff's favorite resolver sitting underneath the desk here in front of me, or Google's public DNS resolver, you know, handling gazillion of queries per second. And when we talk about resolvers, the small numbers, the small resolvers tend to overwhelm the large ones if they all get a weighting of 1. And this is why what we saw is that 1400 is now used by 7% of users as distinct from, you know, resolve accounts, which is kind of different.
Yeah, so I think we did the analysis mostly for 1222, but I can't look into that exactly. Yeah, you're right. Yeah. So, and for that now, I think we run another research with folks from New Zealand, and they confirmed the same. 1/3 of our queries come from Google and Facebook and other Facebook and 3 other systems, Microsoft and Amazon, and I forgot the other. But Google Public DNS is our biggest client by far, and this is public information as well. But altogether, these 5 networks, they account for 1/3 of our traffic, but the other 1/3 is not. But yeah, I have to look into that in the 1400.
It's just this major challenge when any of us try to measure the DNS of trying to actually understand how to make the results meaningful. Because as I said, there are massive resolvers and there are tinsy-winsy resolvers.
Yeah.
And equally, when we even try to think about users, caching gets in the way and we have a very dim view.
Yeah.
And so, you know, I think we're both down the same path of trying to understand how to get a decent picture from what I would tend to say is cloudy data.
Yeah.
Thanks anyway. Great work.
Yeah. Thanks, Jeff.
Thank you, Jeff. I see we have another raised hand from, which is Puneet Sood from Google. Puneet, go ahead.
Hi, Giovane. So thanks for running this experiment and the presentation. This is good to see. Just to also to respond to Jeff Houston. So yes, Google Public DNS was running with 1400. The main point I would make is that this was not so much a flag day, it was more a slow change in behavior for us as well as I assume a bunch of other operators. So it'll be good if you could repeat this experiment now and see how the data looks.
Can do that, yeah. So this is well, this is for the paper, but I can easily rerun the queries and post them on Mattermost or somewhere else.
Thanks. So I have a question in the Q&A facility from Peter Koch. Something I would like to ask as well. Some RR sets are riskier than others. Do your data allow an assessment for DNS key in particular?
So we are analyzing anything that comes out of our servers, like all the responses, regardless of the query type, whatever comes out, we take that into account. So put it all together in the same bucket, if that's what he's asking. We don't discriminate. We get all the traffic,
Yes.
I can go back here in the table and probably can see that. So for example, in July 2020, we had this number of queries, 45 billion and 45 billion responses.
Yes.
And whatever it is, we analyze.
Yeah, yeah. Yeah, but I mean, your slides suggest that it doesn't occur that often, fragmented data, but for some records, it's more important than for others, right?
Yeah, yeah. So when you take a bulk of queries that we see that are now, it doesn't happen very often, no. Fragmentation, no. But I think it's in the paper, if I'm not mistaken, the query that generates more, the larger response for that NL that we look like analyzing our passive data. I think it was any, or I'm not quite positive. I would have to look into that, but it's in the paper. There are far more details in the paper.
Thanks. Thank you, Giovane. There are a few more remarks in the Q&A from Stefan Ubbink. He says, the DNS flag day only is that the software uses the new setting as a default. As far as I know, the day does not mean it has changed on systems. That's right.
Yeah, and I think like we documented the paper where when bind started using that, but they have this dynamic value too. So they kind of try to assess.
Yeah.
Unbounded probably does something similar, I would guess.
Yes. We changed it on the day, but you know, it takes a little while until people are installing the software.
Yeah.
And a final remark from Brian Summers. For the record, OpenDNS sets the buff size to 1410 and has done so for many years.
So that's kind of nice, getting now we can fingerprint all these resolvers on the buffer size.
Indeed, 1410 is OpenDNS. Thank you very much, Giovane.
Thanks
it
a
was
lot.
very interesting.
Thanks, everybody.
So we will now have a break for 15 minutes and start again at 6 o'clock UTC. I would like to remind you that there are the breakout rooms for face-to-face chat, spatial chat. You have received details in how to enter that in the email in advance, or you can see the details on the rolling slides, which will follow shortly. Please do not share the spatial chat link with anyone else. And I'd also like to thank our sponsors again, Farsight Security and VeriSign. And I see you at 6 o'clock.
Okay, welcome back to the final session of OARC 35. Thank you if you've stuck with us this long. We try not to take up too much time, but we'll like to spend a little bit of time at every other workshop or so, letting you know how things are going at OARC and what we've been up to. I did a brief introduction for non-members yesterday. Here's a bit more content that's hopefully relevant to members. Basically, it will be myself standing in for Jerry. Jerry, unfortunately, hasn't managed to stand the pace of the weird time zone. And then Matt will be giving a systems engineering update, and then finally I'll give you a little bit of overview on organizational information. So hopefully 45 more minutes, and then you can all go off and enjoy your Fridays or your weekends. Before I start, I'd like one more time to thank VeriSign and Farsight Security as our sponsors this time, and also a big thank you to all the speakers who have been speaking this far. So I know you'd all much rather listen to Jerry than me. The important thing here is that when we do our regular quarterly reports to the members, we also do them in written version for the workshops. So you will be able to find Jerry's written report linked to this particular item. Sorry about the helicopter. Any mistakes that you see in the following are mine and not Jerry's. So what have we been up to in the software front? There's funded projects. There are some highlights and updates about the software. And the other thing is that in the written report is that we always ask the members what they've been up to with their mostly open source software projects. So there's thank you all the members that contributed to that. There's news about that in the written report as well. You can find all the software that we have at the web page that's listed there. Shows all the software. You can see there's a big list of tools which we have taken on board and or developed ourselves. There's also information about funding development work, our licensing policy, and links to the various GitHub projects and mailing lists that we have. 18 releases have been done since OARC 33. So, you know, just maintaining the regular releases is becoming an increasingly big part of what we do, and more about that later in terms of increasing our software engineering headcount. There's been 160 issues and pull requests that have been resolved and or merged in. You can see the activity level here, which is pretty steady, but it's it's good that we get the engagement and the support to the various tools from the community. Funded projects, two important ones here for 2021. There is the DNS-Perf DNS-over-TLS project, which has been funded by Mozilla and Comcast. The first phase of that was to remove dependencies from some internal libraries of bind that were used by DNS-Perf originally. It now uses entirely open and public libraries and library interfaces to various pieces of code. That was the first phase. The second phase was to add improved support for stateful transports, so it works better for connection-oriented DNS over TCP in various forms. And then the third part, and the third part we'll see a little bit more in a minute. Check My DNS is a tool that's been around for a while, our modern DNS tester. There were some RPKI features added to it on an ad hoc basis some time ago. I'm pleased to say that we got a second year of our community grant funding, and we were able to use this to add the user interface for the RPKI origin validation in the form of achievements, and achievements are a badge which has been added to Check My DNS, that we can potentially use for other test results as well. Other highlights, there's now a dedicated software channel on the Mattermost server, which seems to be getting a lot of activity and engagement. So you'll certainly find that useful discussion, and also you can get some help with your use of OARC software. DNSCap, there's a version 2.0.0 release has come out. DumDumD is one of the components of our software suite. It's had some additional features added to it to help it work better with the DNS-Perf work that's been done. And the DSC Grafana tools, the example graphs have been updated and fixed. What we're going to be working on in the future, phase 3 DNS over HTTPS support is going to be added to DNS-Perf between now and the end of August. Jerry is thinking about doing a crash course on how to use DSC and Grafana, and that would be something that we could add on to OARC 35A. So please do let us know if you're interested in that. It basically be a tutorial setting up from scratch to generate the graphs. And if you've got ideas for things that Jerry could be working on, then please let him know, and we'll be happy to take that on board. This is the point which we usually get questions. I have a strong suspicion that if there are any questions, they will probably be better answered by Jerry than me, but I'll certainly do my best. I also apologize that my voice is starting to give out after staying up half the night. Okay. If there are no questions, which there do not appear to be, I will now hand you over to Matt, and Matt will give you the update on the systems engineering.
Hi, everyone. Yes, I'm Matt Townsett. I'm a OARC systems engineer. Let's get slides going. All right, so as Keith mentioned, there's a written report that sort of accompanies this. The URL for where to find out Indico is there, as well as a QR code that will take you to it. So the report, in addition to the stuff I'm talking about here, the report goes into some more detail about those things, but also includes a bunch of things like overviews of the services that OARC has, and the data that we store, and sort of how to a little bit about how to get at that stuff, and what you can do with it. So as we've mentioned at a couple of previous workshops, we're on the lookout for a bit of headcount related to systems and network engineering. We were looking for somebody to sort of be an on-call person on site where in Fremont, where the bulk of our systems and network is. Now that the sort of pandemic travel restrictions look like they're probably coming to an end in the next few months, we're finding that to be a little less urgent, although we would like to still have somebody that we can go to for emergency type work, so that we're not constantly bugging volunteers in the area. But we're also still looking for somebody to do some specific short-term network engineering work around cleaning up the configs on our Fremont and Ottawa routers. But we're also looking to replace those routers this year. And just to sort of get some of the time-consuming stuff off my plate, we're looking for somebody who can help out with the taking our requirements and budget information and convert that into not only some procurement suggestions, but also to take care of the initial implementation and conversion of the existing configs over to a new platform. So there's more information about that stuff on OARC's careers page, and you could also talk to me or Keith about that. In terms of new systems and networking work that's gone on, I've been working on some new DNS infrastructure. OARC, I made the joke in the written report that OARC really has been, the absolute epitome of the English adage about the cobbler's children having no shoes. Our own DNS infrastructure has been really falling behind for a long time. We've basically been running shell scripts that were written many years ago in order to do all of our zone signing and no key management whatsoever. So I've got a new hidden master in place there, which we have started migrating zones over to. The first one to go on that, though, was the zone for DNSViz.net, which we finally migrated authority for from Sandia National Labs over to OARC. That was sort of in response to some issues we had trying to do some migration on some maintenance on the DNSViz site a few months ago, where we found it was really difficult to make short-term changes to the zone in order to do things like redirect the website to a maintenance page, that sort of thing. So we got that zone moved over. It was the first one to be imported into the new DNS server, and I'm beginning to migrate OARC's other zones over to it. The big thing that's going to come out of this once it's done is I'm finally going to be able to do algorithm roles for OARC zones to get off of the old algorithms that we're using. We also have we have a new bit of infrastructure for doing server installs. So this was something I was already kind of looking at for the Ceph storage cluster, which is coming up later in the presentation. But we had an issue, which I'm also going to talk about in just a moment, with the analysis servers this year, earlier this year, which kind of brought this, made this a bit more urgent. So essentially what this is, it's a tool that's very similar to older things like Kickstart and Jumpstart for doing sort of rules-based installation of OSs on systems using TFTP and things like that in order to get an installer and kernels running and stuff. But it's really neat in that it allows us to sort of define classes of things that can be combined in different ways in order to create a rule set for any given server. So I can define classes that relate to the different types of hardware we have and the different types of services that are provided, and sort of the combination of those two types of classes produce a rule set for the given server for how to divide up the disks and what things need to be installed initially and that sort of thing. So we have this up and running, which is now going to be going to make things a lot easier for when we need to do server replacements and large significant upgrades to operating systems and that sort of thing that sort of can't easily be done just through a normal upgrade process. So the analysis server thing, which I mentioned, they've been due for an OS update for a really long time, but it's been really hard to get time to do that partly because they're pretty much constantly in use, but also that hardware is aging and it's making it very difficult to use sort of the more standard OS install techniques, particularly remotely, in order to get OSs on them. So the very old Java-based remote console, which has been a problem for the last couple of years because the plugins that it depend on have been deprecated in web browsers for a very long time. But we even started running into new problems lately because, believe it or not, they are so old that the standards for transmitting keyboard keystrokes across that kind of connection had changed. And so even just getting through the OS installer was really hard and even impossible in a couple of places. We're also running into problems where current OSs no longer have the drivers necessary to run things like the old network cards on those machines. So having this FAI fully automated installer up and running in order to do this was really important and really helpful. So now that we have those machines on new OSs that can actually be maintained, we've instituted a new maintenance window on the 1st and 3rd Tuesday of every month between 3 and 7 p.m. UTC. So if we need to reboot the servers for any reason, that's when we'll be doing it, new kernels, that sort of thing. And we won't be announcing those reboots, but we will be using the sort of on-system facilities to notify anyone who's currently logged in that the reboot will be coming. So we recently completed the 2021 Day in the Life collection. So when I put together the report and these slides, we were still receiving the sort of long tail of uploads from some contributors. I think that's all done now. The last time I looked, which was earlier this week, we had about 13 terabytes in from about 22 contributors. So it's down a little bit from last year in terms of the volume of data, although we have one additional contributor. I sort of suspect that's just due to different usage patterns now that we're sort of, stabilized in the pandemic. But yeah, it'll be interesting to see what comes out of that once researchers get a look at that data. So we'll start post-processing for that soon, and we expect that the data will be available for researchers probably in about a month. There's a bit of pre-work that needs to be done before we can start that processing. Something I've brought up a few times in the last few workshops is the shared DSC platform. For a long time, OARC has been collecting DSC data from members and putting it up in a way and sort of a shared DSC viewer so that people could sort of compare DNS traffic among members. But with the new OARC portal that we put in place about a year and a half ago now, I guess, a little more than a year and a half ago, there hasn't actually been a way to view that data. And we've asked for feedback from members a few times about what we should do with that and haven't really heard anything. So we are planning now to discontinue collecting that data. RIPE NCC is now the last member other than OARC to be contributing data to it. So we'll be in touch about shutting that down sometime soon, I think. As I mentioned, our OARC's routers, the routers that OARC is using are now beyond end of support. It's quite old hardware that we've got. The very last OS update to ever be released for this platform came out at the end of the year, and it has been applied. This unfortunately didn't fix an ongoing routing issue we've been having in Fremont, where we seem to be randomly losing individual V6 routes. So we're really going to be relying on getting a new routing platform in there in order to fix that up. We are also planning on expanding our network infrastructure a bit. Namely, we've had an offer for a very reasonably priced second transit connection, which we would like to bring up, but of course we need new routing hardware to manage that. So I'm out of time here. So a very quick rundown on our new Ceph storage cluster. There's the original plan for this was documented at OARC 31. So there's the report there that talks about sort of the justification and the issues we were having and the ideas I had at the time about how moving to a clustered storage infrastructure would help us. So we're sort of in the last stages of that now. It took us a long time to deal with getting funding and getting the hardware ordered and actually delivered, but the final hardware actually showed up in very late November. We had a contractor on site who dealt with racking and cabling the bulk of that. Unfortunately, our fiber switches for the 10 gig cluster network didn't show up until after that work was complete. So we did finally get them racked up in Q1, thanks to the help of the remote hands in the NOC at the data center. Cabling for that we're going to do pretty soon, and we're expecting to basically have this in production by the end of Q2. So that should be really nice to have. It'll improve life for a lot of people who are doing work on our analysis servers. Questions for anyone? So not hearing anything from Keith.
Any questions for Matt?
Sorry. There don't seem to be any questions, and
all right.
No raised hands either. So over to you, Keith.
All right, thanks very much.
Okay, so last presentation of the day. Just want to give you a brief update of what we've been up to since OARC 34 in the past 3 months or so. I commend you to the written reports. Apart from not being delivered by half-awake people, you'll find a lot of detail in Matt's and Jerry's report and sort of general overview in my written report. These are all accessible from Indico. So if you want to read it in time and digest it and ask us any questions, we'll be happy to do that. So President's quarterly report on where we're at with OARC, what have we been doing while the world has been twiddling its thumbs in pandemic mode. OARC 35 was very well attended. Sorry, 34, I should say, sorry about that. Last workshop was very well attended, 180 attendees, so that was great. It was really good to get that level of engagement. As Matt said, we completed the Digital 2021 collection pretty much. Still waiting on a few more uploads, but it looks like a decent update. Software front, major updates to DNSPerf and Dnstap. Not only did Matt do major software upgrades to the analysis servers, but he built maintenance automation, which we will use to complete new data store installation and also make a lot of our systems management better. We've I already mentioned the Check My DNS Tester improvements. And the other thing is that 2020 was a tough year to get through in many ways, but we actually finished up in a very strong position financially. We got a lot of good support from members, donors, grants. So I'm pleased to say that lets us do more things going forward. And I also think that the fact that we kept things running and the industry kept the internet running and that we were able to do some successful online events through Euro pandemic is no short an achievement. And I'm very proud of our staff and very grateful to our community for letting us do that. About a year ago, we came up with a strategy for here's how we're going to cope with the pandemic, and the strategy is still pretty much in place, and we'll be there until we come out the other side. Really, the main change is that while we were figuring out how to run our events for everyone stuck at home a year ago, now we're starting to think about, at some point there will be physical events again. How do we get back to these? How do we run them in a hybrid fashion so that when some people can participate and others cannot, that everyone's there on an equitable basis? So that's the main thing that we're thinking about, is sort of the next step of the pandemic strategy. But yeah, I mean, going into this workshop, I kind of felt, we finally got the hang of this thing, this pandemic thing. They're running the fully online workshops. I think everything is gone really very smoothly over the past couple of days, and that's because a lot of work has gone in to preparing everything and running things to how we figured out doing it. And even though as a team, remote work from home stuff was something that we've been doing for a long time before we all were forced to do it, we still miss everyone. We really miss seeing you and engaging with our community and everyone. I think that we have gathered for posterity a couple of interesting day in the life of the internet annual data sets, which should provide interesting context on all of this events over the past year or more. And the other thing as well, one thing I don't think we've completely got the hang of is taking care of ourselves. Yeah, staying up to weird time zones like this is perhaps not the best way of doing that. But it's a learning journey, I think we all know that. It's certainly not just the OARC team that has had to learn that. Support has been strong. Thank you to everybody who has contributed to OARC, both financially and materially, and with your time and moral support. And yeah, jet lag without the air miles, the myriad idiosyncrasies of Zoom, which still managed to catch all of us out despite the amount of time that we spent on it. And yeah, we kind of still have fun stuff like space penguins and other mascots. So we're still signing up new members. Very pleased since the last workshop to sign up Deutsche Telekom as a bronze member, one of the biggest carriers in Europe. Netscar Arbor also as a bronze member. Very pleased that GoDaddy have upgraded their membership from bronze to gold, and Kaida have been able to upgrade from supporter to blue level. And like I said, strong support. Nobody who's a paying member has terminated their membership or downgraded their membership. So that's really awesome. We really appreciate that. We did very well with grants last year. The grants that are still running in 2021 are the ones that we've mentioned already. So a big thank you to Mozilla Open Source support and the Comcast Innovation Fund for making the DNS-Perf DOH work possible, and to Aaron Community Grants Program. We've listed all of the grants that we received and donations that we received over the past couple of years at this grants page. So you can see there's good support there. And I mean, if you're interested in funding us to do a specific work or to make a donation, we'd love that. But thank you to everyone that supported us. And I mentioned yesterday that there's a couple of people that we want to show special appreciation for, and for Shumon, we did that yesterday. I don't think George is out there, but hopefully he will get the vibes. George served on the OARC board for 6 years, between 2014 and 2020, and then for the latter part of that is the chair. So I'm afraid we cannot present him in person, but here is the award that we sent him, and here is his fine self. So and we're in his time zone. So thank you, George. It was a pleasure to work with you. Back to some more administrative stuff. I'm afraid the past year, some businesses in the service office-based business haven't done so well. Others see it as an opportunity for the future. So we have this little office in Indianapolis because banks and government agencies want us to have a physical location. And we have some of the old paperwork that we still need to store. So I found a new location, and from the 14th of May, we'll be moving into that. It does not really have any material effect on how you deal with OARC. We have a separate PO box in California that if you need to send checks or invoices to, that stays the same. Really, this is just for the record to let you know, if you see this address, that you're not blindsided by it. The other thing, as I mentioned, we're in a strong financial position. We have far too much to do. I really feel for Jerry and Matt with all the stuff that they need to support. So we're hiring. The way that we're doing this is that we have a couple of specific projects. Matt mentioned the network, the router config cleanup project. And we want to get the third phase of the DOH for DNS-PERF project preferably finished off by somebody who enjoys and has good abilities with HTTPS. So these are the two short-term projects that are mentioned there. But we have budget for both of these positions, essentially duplicating Jerry and Matt on a long-term basis as well. And we're interested both in applications for the long-term position, but it is possible that if people are the right candidates for the short-term projects, we may engage them on a long-term basis. We also have 2 non-technical positions to fill, membership coordinator. So again, Sue's role there, beefing up that, and administrator, somebody who can help with some of the more routine paperwork and other administrative tasks that keep the organization working. All of these roles are on a remote work from home basis. You can find more background about them there, and that's where applications go. So if you know anybody that might be a good candidate, please encourage them to apply. The team has worked really hard over the past year. It's been challenging. One of the things that we did last year was we gave them some downtime, so they can. Nobody's getting any vacation much at the moment, but at least if we can all shut off at the same time, we can give everyone a break. So for next week, we'll be doing a one week shutdown. I mean, obviously, all the online services will continue to operate, and we'll be monitoring email and voicemail just in case anything emergency comes up, urgent, requiring escalation. But if you can all grant us that time off with our families and just to switch off a bit, we appreciate it. I mean, thank you for your understanding of the sort of circumstances I've been working under for the past year. All your support and patience is very much appreciated. And I really appreciate the team. I mean, everybody has stuck to it and done some tricky things and pitched in for things that may not necessarily have been their ideal choice. And we're here and we're in a strong position, and we intend to look after our precious team resource and keep it functioning. So next workshops, I sincerely hope the next time that we do a workshop that there will be at least some of us meeting in person. We set the plan for the first 9 months of 2021 that we would not do any physical workshops. We expect that probably over the summer we'll do a short online event, the sort of format that we did for short events last year, maybe around August. The plan for Q4 is that the AGM we will be doing on a hybrid basis. Ideally, we do that in October and not make it too late in the year. And then all the good opportunities for doing the OARC 36 come up in November for various reasons. A lot of September and October, it's very difficult to get space anywhere. In November, we may co-locate with NANOG or UKNOF or RIPE, possibly even IETF, just depending on how it goes. We're confident that by February next year, we will be able to do a physical meeting, and we have a deposit and confirmed booking in Austin, Texas to co-locate with NANOG in February again. Anyway, I mean, we know that what you want to do and what you're able to do are not necessarily the same thing. So in this survey for this event, there's a bunch of questions about what you think you might be able to do, or what you might be able to do, what you want to do. So if you can give us feedback, even if you don't have any feedback on this event, which we would very much welcome, we'd still really like to hear your feedback on what the options are for meeting frequency, duration, online versus offline, and then when we might make that transition. So it just really falls on me to wrap things up with the usual pleasure of thanking everybody. I'd particularly like to thank VeriSign and Farsight Security for being our meeting sponsors this time. All of the OARC members and supporters for supporting us through this, all the grant and donor funding that I already mentioned. The program committee have been awesome. We have a smooth meeting. They spend a lot of time in rehearsals and putting together the program. So I'd particularly like to thank the program committee members that have volunteered this time. So Jake, Pallavi, Willem, Manu for their session chairing and Q&A monitoring, and also Huyen as our guest timekeeper, and Maurizio, who's been working hard with keeping the Twitter feed and the social media stuff running throughout the meeting. Big thank you to all of our speakers who have, they do this all in their own time, and they've been doing this at strange times of day this time around. It was great to see that we got some good contributions from the Asia Pacific region of our members and speakers. So thank you all for that. Just making sure I don't forget anybody, but yeah, I'd just like to thank Matt and Dinesh for all the logistic work that they have done for this meeting, and Jerry and Sue for the support behind the scenes and all the prep that they've been engaged in as well. So if you like OARC workshops, there's an opportunity to sponsor them, even when we're doing them online, or maybe you would like to engage in patronage for all our workshops for a year, or just a donation. There's various ways that you can do that. But again, big thank you to everybody. And with that, that is basically the end of what I have to say. I'll be happy to take some questions if my voice holds out. If not, we will, as I say, I hope that next time we will see at least some of you in person.
I can't see any questions submitted, and no one's raised their hands.
Everybody's gone to sleep. There's no questions.
So any questions, anyone? Now's the time. Oh, we have a raised hand. So it's Mark Andrews. And Mark, you may unmute yourself. Please go ahead.
Yeah, just thank you. Yeah, it's nice to not being up in the middle of the night trying to have one of these meetings.
Yeah, now we feel your pain. Thank you, Mark. It's a pleasure.
Thank you. We actually have one more. Hold on a second. And we have Benno. Okay, Benno, please unmute yourself.
Yeah. Not a question, just a word of appreciation. Oh, as Keith presented, it has been a difficult year for all of us, but I want to specifically address the DNS-OARC team. You did a great job, and I think I can speak for the other board members also. We are very happy how you managed to work through the year and, well, achieved great results, good online attendance of the OARC meetings, and also as a board you also look a little bit to the finances, and indeed we had a very good healthy financial year. So Keith, Dinesh, Matt, Jerry, all the teams too, thank you very much.
Thank you, Benno. Thank you.
Yeah, a pleasure. You're
Thanks
welcome.
very much.
We do have some more, so let me have a look. There's some comments that came through, and there's another raised hand, so I'll come to that shortly. There's comments, all of them actually saying thank you. Same from me, great to be in daylight hours, so seems like we've done something right here for a section of the world. Also, Davey Song says thanks for organizing the online meeting, especially for Asia people. Marco Diaz, thank you guys, great work. And I'll go to Ali Reza Saleh, who wants to talk. So you may talk, unmute yourself, Ali Reza.
Yep. I just want to say thank you, to everyone, to the DNS-OARC to have a great work. And I just also have another question. I'm originally from Iran. I just wanted to know that is it any possibilities that actually DNS-OARC can support that .ir or that Iran? This is that most that more like that administrative question. Thank you.
Yeah, I thank you for your kind words. I appreciate it, and I also understand the challenges. The short answer is I don't know. We all live in a geopolitical environment that it would be nice if everyone was nicer to each other and we didn't have to live with all the challenges. But yeah, we can take that discussion offline and we can investigate it and see what's possible.
Okay, thank you, Ali Reza.
Thank you.
Okay, well, it doesn't seem that there are any more. They were all comments rather than, generally they were all comments rather than questions. But thank you, everyone. Back to you, Keith.
Yeah, no, thanks, Dinesh. And thank you, everyone, for your kind words. And I think that we will wrap things up. Just to remind everyone, we'll be closing the spatial chat room at the same time as the Zoom room. So I wish you all a good weekend, and we will see you online. Thanks.